Imagine taking something like our Sun, with all of its light and warmth, and letting it collapse until it was no larger than a planet. What's left behind is a quiet stellar remnant, so dense that a small piece of it would be heavier than anything you could imagine on Earth. This is not a myth or a monster, but a real object shaped by deep time. This is a white dwarf. It's a place where atoms themselves have given way to pressure, and gravity has settled into a quiet truce with the rules of the quantum world. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This is a journey to understand one of the most common final stages of a star. The vast majority of stars in our galaxy, including our own Sun, will one day become one of these cosmic embers, shining with their last remaining warmth. They are not failures or mistakes, but simply a different kind of existence. How can something so heavy be so small? And what happens when the relentless force of gravity meets a quiet, unmovable objection from a world we can't see? This is the story of a star's final, peaceful form. The life and times of a sun-like star. To understand how a star ends, we have to understand how it lives. Every star in the night sky is in the middle of a long, slow balancing act that lasts for billions of years. It's a quiet conversation between two forces. On one side is gravity, always pulling everything inward. A star holds an incredible amount of matter, and all of it is trying to pull itself into the smallest possible space. Without something pushing back, a star would simply disappear into itself. That push comes from its core. Deep inside a star, the pressure is so great that hydrogen atoms are fused together to create helium. This process releases a steady flow of energy, which moves outward from the core. This outward pressure is what holds the star up, resisting gravity's inward pull. For billions of years, a star like our Sun exists in this calm state of equilibrium. The outward push of fusion perfectly balances the inward pull of gravity. It is stable, it shines, and it waits. Our Sun has been in this phase for more than 4 billion years, and it will stay here for about 5 billion more. But this balance cannot last. The hydrogen in the star's core is not an infinite resource. Over time, it is used up, leaving behind a growing core of helium. When a star like our Sun runs out of hydrogen fuel in its center, the engine that supported it begins to quiet down. The outward pressure fades. With nothing holding it back, gravity begins to win. The core starts to collapse under its own weight. This collapse, however, starts a new and much shorter phase in the star's life. As the helium core shrinks, it gets much hotter. This new heat ignites the shell of hydrogen that still surrounds the core. This new burning is far more intense. It generates a powerful wave of energy that pushes the star's outer layers outward. The star begins to grow, swelling to 100 times its original size or more. As its surface expands, it cools, and its color shifts from yellow-white to a deep red. The star becomes a red giant. When our Sun reaches this stage, it will grow so large that it will consume Mercury, Venus, and possibly Earth. The final chapter for our planet will be to quietly vaporize in the atmosphere of its dying star. Inside the red giant, the core continues to shrink. Eventually, the temperature reaches a critical point, around 100 million Kelvin. At this temperature, the helium, which was once just waste, becomes new fuel. Helium atoms fuse into carbon and oxygen. This new fusion provides a temporary source of outward pressure, and the core's collapse briefly stops. But for a star the size of our Sun, this is the last step. It doesn't have enough mass to start fusing carbon and oxygen into anything heavier. Eventually, the helium fuel runs out. Fusion in the core stops for the last time. The star's time as an engine is over. What happens next comes in two parts. The outer layers of the star, now loosely held, are gently pushed away into space. This expanding cloud of gas and dust forms a planetary nebula. The name is a historical mistake. They have nothing to do with planets. They are simply the star's last, beautiful sigh. And the core left behind? It's a small, incredibly hot sphere of carbon and oxygen. With no fusion left to support it, it faces its final collapse. Gravity, the force that shaped its entire life, takes over completely. The star's heart begins to fall inward, setting the stage for one of the strangest transformations in the universe. The inevitable collapse. A problem of gravity. The engine is quiet. The fuel is gone. The long conversation between fusion and gravity is over. The stellar core, a sphere of carbon and oxygen, is now alone. Imagine the mass of our Sun, 2,000 trillion kilograms, in a space that is shrinking every moment. This is the quiet, inevitable result: gravitational collapse. In a normal star, atoms are mostly empty space. Electrons orbit their nuclei at great distances. But under the pressure of a collapsing core, this structure begins to break down. The force is so great that electrons are stripped away from their nuclei, creating a dense soup of separate particles. But the collapse continues. Gravity squeezes this material tighter and tighter. The particles are forced into a space so small that it stretches our idea of what matter can be. The density becomes enormous, 1,000,000 times greater than water. A single sugar cube-sized piece of this material would weigh a ton on Earth. Think of it this way. Imagine all the people on Earth being compressed until they fit inside a single thimble. The pressure would be difficult to comprehend. Now imagine that on the scale of a star. All the atoms from a body over 1,000,000 kilometers across are squeezed into a sphere the size of Earth. As the core shrinks, its gravity gets stronger, which makes it shrink even faster. According to the physics that governs our world, there should be nothing to stop this. Gravity should continue to crush the core until it becomes an infinitely dense point, a singularity. By all classical accounts, the star's remains should become a black hole. For much larger stars, this is exactly what happens. Their gravity is so strong that nothing can stop the final collapse. But for stars like our Sun, something different occurs. Just as the core seems destined to be crushed into nothing, a new kind of pressure emerges. It does not come from heat or fusion. It comes from the strange and quiet rules of the quantum world. This pressure is called electron degeneracy pressure, and it is the only thing that prevents the heart of the dead star from disappearing. The problem of total collapse is about to meet its quantum solution. The quantum stand. A solution from another realm. As gravity crushes the stellar core, it pushes the universe into a place with very specific rules. The electrons, now free from their atoms, are being forced closer together. In our world, there is no hard limit to how close you can pack things. But in the quantum realm, the rules are different. Electrons belong to a class of particles called fermions, and they all obey a fundamental law of nature, the Pauli Exclusion Principle. The principle is simple. No two identical fermions can be in the same quantum state, in the same place, at the same time. Think of a quantum state as a unique address for a particle, defined by its energy and spin. The Pauli Exclusion Principle means there can only be one occupant per address. In a normal gas, there are many available addresses, so electrons have plenty of room. But in a collapsing star, gravity is trying to force all the electrons into the lowest energy states, the most desirable addresses. These fill up almost instantly. As gravity keeps pushing, it tries to force more electrons into these already occupied states. But the Pauli Exclusion Principle says, no. The only option left is for these electrons to occupy much higher energy states. To be in a high energy state means an electron must move incredibly fast. This creates a new kind of pressure. It has nothing to do with temperature. Even at absolute zero, this pressure would exist. It is a purely quantum effect, born from the simple fact that electrons resist being squeezed into the same quantum space. This is electron degeneracy pressure. It is a quiet, powerful, repulsive force that pushes back against gravity. The collapse continues, and the degeneracy pressure builds. The electrons are forced into higher and higher energy levels, creating a stronger outward push. For a time, gravity is still winning. But eventually, a point is reached where the degeneracy pressure becomes strong enough to equal the inward pull of gravity. The collapse stops. An equilibrium is reached, not through the fire of fusion, but through the quiet refusal of electrons to share their space. The star's core, once headed for an infinite collapse, is saved. It settles into its final, stable state. It has become a white dwarf. The pressure has become so great that it has collapsed the atoms themselves, crushing them into a degenerate sea of particles. The matter inside is unlike anything on Earth. It is a strange, super-dense substance held up by a quantum rule. And this new object is one of the most stable and long-lasting things in the universe. Birth of a white dwarf. A new, extreme reality. The struggle is over. What's left behind is the survivor, a white dwarf. It is an object of quiet extremes, a testament to both gravity and quantum mechanics. A typical white dwarf has about half the mass of our Sun, but it has been compressed into a sphere only a little larger than Earth. This is why its density is so great. That analogy of a teaspoon weighing as much as an elephant is not an exaggeration, it is a simple statement of fact. This density leads to another unusual property, its surface gravity. Because so much mass is in such a small space, the gravitational pull on the surface of a white dwarf is hundreds of thousands of times stronger than Earth's. The pull is so strong it would flatten any familiar object into a thin layer of atoms. Any atmosphere it has is pulled into an incredibly thin shell, perhaps only a few hundred meters deep. If Earth had such gravity, our entire atmosphere would be compressed to a height lower than our tallest buildings. The structure of a white dwarf is layered. At its heart is a core of carbon and oxygen created during the star's red giant phase. For stars a little less massive than the Sun, the core might be made of helium. For those slightly more massive, it might be oxygen and neon. Above this core is usually a thin layer of helium, and on top of that, an even thinner layer of hydrogen. Gravity sorts these elements by weight, with the heaviest sinking to the center. When a white dwarf is first born, it is incredibly hot, with a surface temperature over 100,000 Kelvin. But this is just leftover heat. There is no fusion creating new energy. The white dwarf is a stellar ember. From the moment it forms, it begins a long, slow process of cooling, radiating its stored warmth into space. Over billions of years, its bright blue-white glow will fade to white, then yellow, then orange, and finally a dim red. This cooling process is incredibly slow. A white dwarf's small surface area doesn't lose heat very quickly. The degenerate matter in its core is a very good conductor of heat, keeping the whole object at a uniform temperature. But the outer layer acts like a blanket, trapping the heat inside. It will take many billions of years for it to fade significantly. One of the strangest properties of a white dwarf is that the more massive it is, the smaller it is. This feels wrong. In our world, heavier things are bigger. But for a white dwarf, adding mass increases gravity. To balance this stronger gravity, the electrons must be squeezed even closer together to generate more degeneracy pressure. This results in a smaller overall size. This leads to an important question. What happens if you keep adding mass? Is there a limit? The answer is yes, and it is one of the most important numbers in astrophysics. The edge of stability, the Chandrasekhar limit in cosmic bombs. A white dwarf is stable, but that stability has a limit. There is a line that cannot be crossed, a maximum mass beyond which even electron degeneracy pressure is not enough. This threshold is known as the Chandrasekhar limit, named after the astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s. This limit is about 1.44 times the mass of our Sun. Chandrasekhar realized that as you add mass to a white dwarf, the electrons inside are forced to move faster and faster. As they approach the speed of light, the pressure they provide no longer increases fast enough to keep up with gravity. At the 1.44 solar mass limit, gravity wins. Degeneracy pressure fails, and the star collapses catastrophically. A single white dwarf, born from a star like our Sun, will almost never reach this limit on its own. Our Sun will leave behind a white dwarf of only about 0.6 solar masses, safely below the limit. So how can a white dwarf ever reach this point? The answer is companionship. Many stars exist in binary systems, orbiting another star. If a white dwarf is in a close orbit with a companion, its gravity can pull material from that star, especially if the companion expands into a red giant. This stream of gas spirals down onto the white dwarf, causing it to gain weight. Its mass slowly climbs toward the Chandrasekhar limit. As the mass approaches 1.44 solar masses, the pressure and temperature inside the white dwarf's core climb to a breaking point. The core, made of carbon and oxygen that was once inert, is suddenly ready for one final, cataclysmic fusion event. Carbon begins to fuse uncontrollably, all at once, throughout the entire core. This is not a slow burn. It is a runaway thermonuclear explosion. In a few seconds, the entire white dwarf is consumed. The energy released is so great that it completely destroys the star. Nothing is left behind. The white dwarf is gone, annihilated in an event known as a Type Ia supernova. For a short time, a single Type Ia supernova can outshine an entire galaxy. Because they are all triggered at almost exactly the same mass, they all explode with almost the same true brightness. This makes them incredibly useful. By measuring how bright a distant Type Ia supernova appears, astronomers can calculate its distance with great precision. They are standard candles, the cosmic measuring sticks that allowed us to map the universe and discover that its expansion is accelerating. So, the white dwarf exists on a quiet edge. Below 1.44 solar masses, it is a model of stability. But pushed over that limit, it becomes one of the most powerful explosions in the universe. An event that scatters heavy elements across the cosmos and lights up the distant dark. An extreme future. Crystals and darkness. A white dwarf's story doesn't end when it forms. Its existence, which will span trillions of years, is a slow journey toward an even stranger state of matter. The journey begins with cooling. While the surface radiates heat into space, the core, under immense pressure, goes through a phase transition. Much like water freezes into ice, the carbon and oxygen nuclei in the white dwarf's core are expected to stop moving freely and lock into a rigid crystal lattice. The entire core of the white dwarf crystallizes, turning into a single, Earth-sized crystal of carbon and oxygen. In a way, it becomes a cosmic diamond. This is not just a theory. Astronomers have found evidence for this process. The crystallization releases a small amount of heat, which temporarily slows the cooling rate. By observing many white dwarfs, astronomers can see a pile-up, at certain temperatures, a signature that matches the energy released by this mass crystallization. This leads us to the eventual fate of our own star. In about 5 billion years, the Sun will run out of hydrogen in its core. It will swell into a red giant, its outer layers expanding to consume the inner planets, including Earth. Afterward, it will shed these layers, forming a planetary nebula. At the center will be what is left of our Sun, a hot, dense carbon-oxygen white dwarf, compressed into a sphere the size of our planet. It will not be massive enough to go supernova. It will simply begin its long, slow journey of cooling. And what is the end of that journey? What happens after trillions of years? a length of time that makes the current age of the universe feel like a brief moment. After a white dwarf has radiated away all of its leftover heat, it will stop shining. Its temperature will fall to just a few degrees above absolute zero. It will become a cold, dark, crystallized sphere of degenerate matter, invisible in the darkness of space. This theoretical final state is known as a black dwarf. Because the time needed for a white dwarf to cool to this state is far, far longer than the current age of the universe, it is believed that no black dwarfs exist yet. They are objects of the far future. When the last stars have burned out, these black dwarfs, along with neutron stars and black holes, will be among the only things left, quiet reminders of the brilliant stars that once filled the sky. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And feel free to share in the comments what other cosmic mysteries you would like to explore. From a shining star to a red giant, from a beautiful nebula to a dense stellar core, the journey to becoming a white dwarf is a story of transformation. It is a story defined by a quiet struggle between two of the universe's most fundamental forces. For billions of years, fusion holds gravity back. But when that fire goes out, gravity's victory seems certain, threatening to crush the star's heart into nothing. And yet, at the last moment, the universe reveals a final, unexpected rule. From the strange logic of the quantum realm, electron degeneracy pressure emerges and says, "No further." It stops the collapse, creating an object of incredible density and stability. A white dwarf is more than just a dead star, it's a quantum fossil. An Earth-sized sphere with the mass of a sun, so dense a spoonful outweighs an elephant. It shines for eons with leftover heat before crystallizing into a giant cosmic diamond. These stellar remnants are also our own distant future. They are the final chapter for the vast majority of all stars, including our Sun. Studying white dwarfs is not just looking out into the universe. It is looking at what our own solar system will one day become. They are a quiet reminder that even in their end, stars leave behind objects of incredible wonder, showing that in the cosmos, even an ending is a new and spectacular beginning. The slow death of our sun. We see it every day. It is a quiet, constant presence in our lives. It gives us warmth, provides the light that feeds the plants we eat, and has set the rhythm of life on this planet for billions of years. It feels permanent, a symbol of reliability. But this is an illusion. Our sun, the heart of our solar system, has an end. And unlike many cosmic mysteries, we know with quiet certainty how this story will conclude. This is not a story of a sudden, violent end. There will be no supernova for a star like ours. Instead, it is a slow transformation, a story told over billions of years. It is a quiet drama, and we are living in the calm of its first act. We will not be here for the end. In its final stages, our sun will swell into a giant, a star so large it will burn the inner worlds to dust. Then, in a final, quiet release, it will shed its outer layers, creating one of the most beautiful objects in the universe. And at the very end, it will leave behind a ghost. A glowing, dense corpse the size of a planet, destined to cool and fade for trillions of years. This is the story of the slow death of our sun. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The sun today, a star in its prime. Before we journey into the distant future, it helps to understand the star we have today. In astronomical terms, our sun is a G-type main sequence star. We call it a yellow dwarf. But that label doesn't quite capture what it is. Think of it as a star in the middle of its life. It is about 4.6 billion years old, and it has existed in a state of perfect balance, an equilibrium that has allowed life on our world to begin and grow. This stability is not an accident. It is the result of a quiet contest fought deep within its core. At the center of the Sun is a natural nuclear reactor. The temperature is a staggering 15.7 million degrees Celsius, and the pressure is more than 250 billion times that of Earth's atmosphere. In this place, the universe's most fundamental process is unfolding: nuclear fusion. Every second, the Sun fuses about 620 million tons of hydrogen into helium. This is not a chemical reaction, like fire. It is a transformation on a cosmic scale. Immense pressure slams hydrogen nuclei together. Through a process called the proton-proton chain, 4 hydrogen nuclei become a single helium nucleus. But there is a detail here that changes everything. The new helium nucleus has slightly less mass than the 4 hydrogen nuclei that created it. That missing mass, just a tiny fraction, does not disappear. It is converted directly into a colossal burst of energy, following the most famous equation in physics: E=mc². The 4 million tons of matter the Sun converts every second become the light and heat that radiate out into the solar system. This is the energy that warms our world, drives our weather, and powers all of life. A photon of light created in the core today begins a long journey. It can take over 100,000 years for it to bounce its way through the dense solar interior to the surface. From there, it makes the 8-minute trip to Earth. This outward push of energy from fusion creates an immense pressure. It is the only thing standing against the Sun's other primary force: gravity. The Sun contains more than 99.8% of all the mass in our solar system. That mass generates a gravitational force that is always trying to crush the star. So, there is a perfect balance. Gravity squeezes inward. Fusion pushes outward. For 4.6 billion years, these two forces have been in a stalemate. This state is called hydrostatic equilibrium, and it defines a star in the prime of its life. It is this long, stable peace that has given our planet the time it needed to develop. But this peace cannot last. The Sun is an ordinary star. And like any engine, it has a finite amount of fuel. The hydrogen in its core is being used up, second by second. When that fuel begins to run low, the balancing act will fail. And the Sun's slow, certain march toward its end will begin. The first stirrings, the beginning of the end. For now, the Sun remains a steady companion. But the clock is ticking. It has about 5 billion years of hydrogen fuel left in its core. For us, that feels like an eternity. On a cosmic scale, it is the second half of its life. For life on Earth, however, the end will come much sooner. The Sun's aging process is not entirely gentle. As it continues to burn hydrogen, it is slowly getting brighter. Its luminosity increases by about 10% every billion years. In about 1 billion years, the Sun will be 10% brighter than it is today. That may not sound like much, but for Earth, it will be a profound change. The increased energy will begin to warm the planet, causing the oceans to evaporate more quickly. This fills the atmosphere with water vapor, which traps more heat, which in turn causes the oceans to evaporate even faster. It is a feedback loop from which there is no escape. Some models suggest Earth's natural systems might delay the worst effects, but the direction is clear. Earth will become a global steam bath. In 3.5 billion years, the Sun will be 40% brighter. By this point, the oceans will have boiled away. The ice caps will be gone. The intense radiation will strip the remaining water from the atmosphere, leaving our planet a dry, superheated rock, much like Venus is today. All life on Earth will be gone long before the Sun itself begins to die. The true beginning of the Sun's end will happen in about 5 billion years. The hydrogen fuel in its core will finally run out. The fusion engine that powered the star for 10 billion years will stop. In that moment, the great balancing act is over. The outward pressure from fusion is gone. Gravity, held back for so long, finally wins. The core, now an inert ball of helium, will begin to collapse under its own weight. This is where a strange thing happens in stellar physics. As the core is crushed by gravity, its temperature and density soar. It's like pumping air into a tire. As you compress the air, the pump gets hot. The same thing happens here, but on an unimaginable scale. The contracting helium core heats up. This intense new heat radiates outward, into the layers of the star that still have hydrogen. The heat becomes so great that it ignites that hydrogen in a shell surrounding the dead core. Fusion begins again, but not in the center. It now happens in a furious, unstable burn. This shell burning is far more intense than the calm fusion of the sun's youth. The star is now producing even more energy than it did before. This new, supercharged engine pushes the sun's outer layers outward. The sun begins to swell. It grows larger and brighter, entering a new phase as a subgiant. This is the point of no return. The stable, yellow dwarf is gone. The sun has taken its first step toward becoming something else entirely. The red giant, a star unbound. The subgiant phase is only a beginning. The hydrogen shell burning acts like a runaway furnace. The massive surge of energy pushing outward begins to overwhelm the gravity holding the star's atmosphere in place. The sun begins a period of dramatic expansion. Over millions of years, it will swell to a size that is difficult to imagine. It will grow to be 200, maybe even 250 times its current diameter. If you were to replace our sun with this future version, it would be a colossal, looming orb in the sky. As the star's surface expands, its energy is spread out over a much larger area. This causes the surface temperature to drop. The sun's brilliant yellow-white light will fade, replaced by a dull, reddish-orange glow. It has become a red giant. But while the surface is cooler, the total amount of energy it radiates is immense. For the inner planets, this transformation is the end. The sun's expanding outer layers will reach out and consume them. Mercury will be first. As the sun's edge approaches, the planet's rock itself will begin to boil. Finally, it will be completely engulfed, its matter dissolving into the star. It will simply cease to exist. Venus will be next. Its thick atmosphere will be stripped away before the planet itself is swallowed whole. And then there is Earth. Our planet's fate is less certain. As the sun expands, its edge will likely reach or even surpass Earth's current orbit. This would mean our world is consumed, just like Mercury and Venus. But there is another effect. As the red giant swells, it loses a great deal of its mass through powerful stellar winds. As the sun's mass decreases, its gravitational grip weakens. This could cause Earth's orbit to slowly drift outward, away from the expanding star. For a time, it was thought this might be enough to save the planet from being engulfed. But more recent models suggest a different outcome. The sun's expansion may happen too quickly, or tidal forces from its bloated atmosphere could drag Earth inward, sealing its fate. The most likely scenario is that our world will be vaporized. But even if it were to escape, it would be a hollow victory. Earth would be a scorched cinder, its oceans and atmosphere long gone, orbiting a monstrous red sun. Our planet's story will have ended long before. While this is happening, something new begins deep in the star's core. The helium ash, which has been contracting and heating, finally reaches a critical temperature of 100 million degrees. At this point, a new kind of fusion ignites. The triple alpha process, where 3 helium nuclei are fused into carbon. In many stars, this would happen gently. But our sun's core is in a peculiar quantum state known as being electron degenerate. It cannot expand and cool itself down. Instead, the ignition of helium fusion is almost instantaneous and incredibly violent. It is known as the helium flash. In a matter of minutes, an enormous amount of helium is converted to carbon. The energy released is equivalent to trillions of suns. And yet, this enormous event is completely hidden. All of its energy is absorbed by the dense layers of the star above it. From the outside, the only sign is that the star, having found a new stability, will shrink slightly and burn a little less brightly for a time. This calm, however, will be brief. The unraveling, a ghost in the cosmos. The helium flash gives the sun a temporary reprieve, a phase lasting maybe 100 million years. It calmly fuses helium into carbon and oxygen in its core. But this is just a short chapter before the final act. Eventually, the helium in the core is also used up, leaving behind a new, inert core of carbon and oxygen. History repeats itself, but with more intensity. The carbon-oxygen core begins to contract under gravity. It heats up, and this heat ignites the layers above it. Now the sun has a complex structure. A contracting core, surrounded by a shell where helium is fusing, which is itself surrounded by a shell where hydrogen is fusing. This double shell burning marks the sun's second red giant phase. The energy output is colossal, far greater than anything that came before. The sun swells up again, becoming even larger and more luminous than it was the first time. It becomes a bloated, pulsating, and unstable star. These pulses are the sun's death throes. The two burning shells are not in harmony. They create dramatic flare-ups called thermal pulses. With each pulse, the star's grip on its own atmosphere weakens. The pulsations become so violent that they begin to push the star's outer layers off into space. This is not an explosion, like a supernova. It is a slow, powerful process. A series of super winds blows away the sun's outer envelope, carrying nearly half of the star's mass out into the void. This expelled gas forms an expanding cloud around the dying star. Over tens of thousands of years, this cloud grows into a vast, intricate, and beautiful structure, a planetary nebula. The name is an old one. Early astronomers thought these glowing objects looked like planets. They have nothing to do with planets. They are stellar gravestones. The ejected cloud of gas glows with brilliant color. As the outer layers are stripped away, the intensely hot core of the star is exposed. This core, with a surface temperature over 100,000 degrees, unleashes a flood of ultraviolet radiation. This radiation slams into the expanding gas, causing the atoms to glow, much like the gas in a neon sign. Different elements, hydrogen, oxygen, carbon, glow in distinct colors, creating the breathtaking shapes we see in objects like the Ring Nebula or the Helix Nebula. It is the sun's final, beautiful, and temporary masterpiece. The stellar corpse, a diamond in the sky. After the planetary nebula has expanded and faded away, the story is over. All that remains is the object at the center. What was once the core of our sun is now a stellar corpse, an object known as a white dwarf. This is one of the most extreme forms of matter in the universe. It is a sphere roughly the size of Earth, yet it contains about 60% of the sun's original mass. The density is almost beyond understanding. A single teaspoon of white dwarf material would weigh several tons. It is one of the densest objects in the cosmos, surpassed only by neutron stars and black holes. The white dwarf is born incredibly hot, shining with a brilliant blue-white light. But it is a dead star. There is no more fusion in its core. A question arises. What is stopping gravity from crushing it completely? With no fusion pressure pushing out, why doesn't it collapse into an infinitely small point? The answer is found in the strange world of quantum mechanics. As gravity tries to squeeze the atoms and their electrons into a smaller space, it runs into a fundamental law of nature, the Pauli Exclusion Principle. This principle states that no two electrons can occupy the exact same energy state in the same space. Think of it as a cosmic rule. As the electrons are forced closer together, they have to move into higher and higher energy levels, which means they must move at incredible speeds. This frantic motion creates a powerful outward pressure. It is known as electron degeneracy pressure. This pressure does not depend on heat. It would exist even at absolute zero. It is a fundamental resistance built into the fabric of reality that prevents matter from being crushed beyond a certain point. The white dwarf is stable not because it is alive, but because the rules of quantum physics say it cannot collapse any further. From this point on, the white dwarf's fate is simple. It is a stellar ember. It has no energy source, so all it can do is radiate its stored heat into space. This process is extraordinarily slow. Over billions, then trillions of years, it will cool. Its brilliant white light will fade to yellow, then to orange, then to a dim red. As it continues to cool over an almost unimaginable amount of time, something remarkable will happen. The pressure inside will become so great that the carbon and oxygen atoms will lock into a fixed crystal lattice. The white dwarf will crystallize. It will become, in essence, a single, Earth-sized diamond floating in space. Eventually, after a period of time far longer than the current age of the universe, it will radiate away the last of its heat. It will become cold, dark, and inert. A black dwarf. A true stellar ghost, the final, silent remnant of a star that once gave life to an entire system. The life story of our sun is a journey from quiet stability to a raging giant, to the ethereal beauty of a nebula, and finally, to the quiet existence of a diamond corpse. The giver of all life in our small corner of the galaxy will meet a predictable and strangely elegant end. We will not be here to witness the sun's final acts. Our planet and our species are temporary things on this grand cosmic stage. But there is something profound in the fact that we can know this story. That we, a collection of atoms on a small rocky world, can look at our star and understand its past, its present, and its distant future. And in the end, even in death, the sun will be a creator. The elements made in its core and cast out in its final moments will drift through space. This enriched gas, the ashes of a dead star, will one day mix with other clouds, collapse under gravity, and ignite. It will form new stars and new planets. The death of one star becomes the seed for the next. The universe is the ultimate recycler. The story of our sun will end, but the larger story of the cosmos will go on, and the memory of our star will be written into the fabric of worlds that are not yet born. 1 teaspoon of this dead star weighs an elephant. There are substances in the universe so dense, a single teaspoon could weigh as much as an elephant. Not an abstract idea of an elephant, but a living, 5-ton animal, balanced on the surface of a spoon. This is not a myth, not a monster, but the real, quiet end of a star's life. When a star like our own sun uses up its fuel, it leaves behind one of the most unusual objects in the cosmos, a white dwarf. It is a stellar remnant, where the slow, patient force of gravity has squeezed matter toward its final limit, packing the mass of a star into a sphere the size of a planet. But in this quiet battle, gravity does not have the final word. Just as the star's core is about to be crushed into nothing, something else, born from the deepest rules of reality, pushes back. This is a journey into that impossible object. It is the story of a cosmic ghost, a diamond in the distant future sky, and the strange quantum physics that keeps it from vanishing completely. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a city, a forest, or somewhere quiet in between, feel free to share where you're watching or listening from. The long, quiet life of a star. To understand this ghost, we must first understand the life it lived. Every star, our own sun included, is born from a vast, cold cloud of gas and dust. Over millions of years, the gentle, persistent pull of gravity draws this material together. It gathers, it condenses, and as the pressure builds at its center, the temperature begins to climb. It grows hotter, reaching millions of degrees, until a process ignites: nuclear fusion. In this stellar furnace, the most common element in the universe, hydrogen, is forged into helium. This process releases a tremendous amount of energy. It's the energy we see as starlight, the energy that warms our world. But this energy does more than shine, it creates an outward pressure from the inside of the star. For most of its life, a star exists in a state of perfect balance. Gravity works relentlessly to crush it, pulling every atom inward. At the same time, the energy from nuclear fusion pushes outward with an equal and opposite force. This state, known as hydrostatic equilibrium, is what defines a star. For billions of years, a star like our Sun will remain in this stable condition, fusing hydrogen into helium, a serene and steady beacon in the darkness. It is a life of quiet consistency, a slow burn that lasts for what feels like an eternity by human standards. Our Sun has been in this phase for about 4.5 billion years, with another 5 billion years left to go. During this time, known as the main sequence, the star is predictable. It is a reliable engine, converting mass into energy. But no engine runs forever. Its fuel is finite, and the slow depletion of this fuel sets the stage for the end of the star's life, a process that will give birth to the impossibly dense object at the center of our story. The long, peaceful life is only the prelude. The real story begins when the fuel runs out, and the delicate balance between gravity and fusion is broken. The magnificent death and the ghostly birth. For 10 billion years, the Sun will have been a model of stability. But when the hydrogen in its core is gone, the fires of fusion will begin to fade. The outward pressure that held gravity back for so long weakens. And gravity, the patient, ever-present force, begins to win. The core, now made of helium ash, starts to collapse under its own weight. This collapse, however, triggers a new phase of life. As the core compresses, it heats up, and this intense heat ignites the remaining hydrogen in a shell surrounding it. The star, in its final stages, begins to burn its fuel at a furious rate. The energy output swells, causing its outer layers to expand to an unimaginable size. Our Sun will become a red giant. It will grow so large it will consume Mercury, then Venus, and may even reach our own planet. The star that once nurtured life will become a colossal, expanded version of itself, its surface cooler and redder, but its body hundreds of times larger than before. Inside this giant, the core continues to shrink. The pressure and temperature build until they reach a new threshold, about 100 million degrees. At this temperature, a new kind of fusion begins. The helium ash, once waste, now becomes fuel. Helium atoms fuse together to create carbon and oxygen. For a time, a new equilibrium is found. But this, too, is temporary. Helium is a far less efficient fuel than hydrogen, and it burns out much faster, in millions of years, not billions. Soon, the helium is gone, and the core is a dense ball of carbon and oxygen. For a star the size of our Sun, this is the end of the line. It is not massive enough to start fusing carbon and oxygen. Fusion stops for good. With no energy pushing out, nothing can stop gravity. The core begins its final collapse. But something quiet happens to the rest of the star. The outer layers, which had swelled into a red giant, drift away. The star sheds its gaseous envelope into space. These expanding shells of gas, lit up by the hot, naked core left behind, create one of the most beautiful objects in the cosmos, a planetary nebula. It is a celestial smoke ring, a fleeting, iridescent trace of the star that was. And at the very center of this artwork, seen for the first time, is the star's corpse. A tiny, incredibly hot, and unbelievably dense ball of carbon and oxygen. This is the newborn white dwarf. It is the exposed core of a dead star, with the mass of a sun packed into a volume no larger than Earth. It no longer produces energy. It is simply a cosmic ember, glowing with leftover heat, destined to slowly cool for the rest of time. The why? A battle between gravity and the quantum world. Here, the story moves from the familiar scale of stars into the quiet, strange world of quantum mechanics. We have this object, a white dwarf, with a star's mass crammed into a planet-sized sphere. The density is enormous. A single sugar cube-sized piece has a mass of a metric ton. A teaspoon of it would weigh as much as an elephant. The gravity on its surface is hundreds of thousands of times stronger than Earth's. It would seem that this object should not be able to exist. Gravity this strong should be unstoppable, crushing the core until it becomes an infinitely small point. So why doesn't it? Why does gravity, after winning a 10 billion-year war, suddenly stop? To understand this, we need to look closer, down to the level of the atoms. An atom, as we know, is mostly empty space, with a tiny nucleus and electrons orbiting it. Under normal conditions, repulsive forces between these electrons keep atoms apart. It is why you do not fall through the floor. But inside a dying star, gravity is so strong that this repulsion is overcome. Atoms are crushed. Electrons are torn from their nuclei, leaving a strange soup of positively charged nuclei and free-roaming electrons. This is called a plasma. As gravity continues to squeeze, it forces this soup into a smaller and smaller volume. This is the point where classical physics suggests the collapse should continue. But it doesn't, because electrons are quantum particles, and they obey a powerful law of the quantum world, the Pauli Exclusion Principle. This principle states that no two identical fermions, a class of particles that includes electrons, can occupy the same quantum state at the same time. A quantum state is like a unique address for a particle, defined by its energy, location, and a property called spin. The exclusion principle is a fundamental rule of cosmic real estate. Only one fermion is allowed per address. Imagine a large parking garage with millions of spots on different levels. Each spot is a quantum state. As cars, our electrons, enter, they want the easiest spots on the lowest energy ground floor. But once that floor is full, the next car must go to a higher level. It is forbidden from squeezing into an occupied spot. As you cram more and more cars in, you are forced to fill higher and higher levels. The cars on these upper levels have more energy. This is what happens inside a collapsing star. As gravity tries to force all the electrons into the same tiny space, they run out of available low-energy states and are forced into higher ones. An electron in a high energy level moves incredibly fast. Now, imagine trillions of these high-energy electrons, all moving at nearly the speed of light, simply because they are not allowed to occupy the same space as their neighbors. All of this motion creates a pressure. But it's not a pressure caused by heat. It is a purely quantum mechanical effect. This is electron degeneracy pressure. It is the universe's quiet pushback. It's the collective resistance of electrons, a fundamental law preventing them from being crushed any further. At a certain density, this quantum pressure becomes powerful enough to halt the inward crush of gravity. The collapse stops. A new equilibrium is reached, but it is not the gentle balance of a living star. It is a tense standoff. The white dwarf is stable not because it is generating energy, but because the laws of quantum physics themselves forbid its further collapse. This strange pushback is not just a cosmic footnote, it's a reason why matter itself is stable. The chair you are sitting on holds its shape because the Pauli exclusion principle prevents the electrons in its atoms from collapsing into each other. What we see in a white dwarf is this everyday principle, amplified to a cosmic scale. The universe is filled with these hidden rules, these deep physical laws that create the reality we see around us. Life on the edge of possibility. So, what is this ghost of a star like? A white dwarf is a truly alien world, governed by physics at its extreme. When it is born, a white dwarf is incredibly hot, with a surface temperature over 100,000 Kelvin, far hotter than our Sun. It shines with a brilliant blue-white light. But because it is so small, only the size of Earth, its total brightness is quite low, which makes white dwarfs difficult to find. The nearest one, Sirius B, is the companion to the brightest star in our night sky, Sirius A. For decades, astronomers saw Sirius A wobble, as if tugged by something massive but unseen. It wasn't until 1862 that the faint pinprick of light that is Sirius B was finally observed, hiding in the glare of its sibling. This slow correction tells an important story, not just about Sirius B, but about how science works. Understanding evolves as new data appears. The most unfamiliar property of a white dwarf is its surface gravity, which is about 350,000 times that of Earth. If you could stand on its surface, you would be instantly flattened into a thin layer of atoms. The escape velocity is thousands of kilometers per second. Even light struggles to leave. As photons climb out of this deep gravity well, they lose energy and their wavelengths stretch. This effect, called gravitational redshift, was predicted by Einstein's theory of general relativity, and measuring it from stars like Sirius B helps confirm their incredible density. This intense gravity sorts the elements like a cosmic centrifuge. The heaviest elements, like carbon and oxygen, sink to the core. Any lighter elements, like hydrogen or helium, float to the top, forming an atmosphere only a few meters thick. Perhaps the most poetic aspect of a white dwarf is its fate. It has no fuel, so it shines only by radiating away its leftover heat, like an ember from a cosmic fire. Because its surface area is so small, this cooling process is extraordinarily slow. The universe, at 13.8 billion years old, is not yet old enough for any white dwarf to have fully cooled. But in the distant future, trillions of years from now, long after the last stars have burned out, the white dwarfs will finally radiate away the last of their heat. As they cool, the carbon and oxygen nuclei inside will slow down and lock into a rigid crystal structure, much like water freezing into ice. The white dwarf will crystallize, becoming a solid, Earth-sized diamond. Eventually, it will cool completely, fading to the background temperature of the universe. It will become a black dwarf, a cold, dark, crystallized remnant, drifting silently through the eternal night. This is the final fate of stars like our Sun. Not a spectacular explosion, but a slow, graceful fade into darkness, leaving behind a jewel as its final legacy. Though, because the time required is so much longer than the current age of the universe, we believe that no black dwarfs exist yet. The critical threshold, the Chandrasekhar limit. The story of the white dwarf is one of a quiet stalemate between gravity and quantum mechanics. For most, this is their fate, a slow cooling into a black dwarf. But there is a twist. This quantum pressure, as powerful as it is, has a limit. In the 1930s, a young astrophysicist named Subramanian Chandrasekhar, on a sea voyage from India to England, made a remarkable calculation. He asked a simple question. What is the maximum mass that electron degeneracy pressure can support? As you add mass to a white dwarf, gravity gets stronger, and the electrons are squeezed tighter. They are forced into higher energy states, moving faster and faster. But there is a universal speed limit, the speed of light. As electrons approach this limit, the amount of additional pressure they can generate begins to diminish. Chandrasekhar calculated the exact point where this resistance would fail. He found that if a white dwarf's mass exceeds about 1.44 times the mass of our Sun, electron degeneracy pressure is overwhelmed. Gravity wins. This critical tipping point is now known as the Chandrasekhar limit. A single white dwarf born from a Sun-like star will almost always be below this limit. So how could one ever cross this threshold? The answer is companionship. Many stars exist in binary systems. If one becomes a white dwarf, it can begin to pull matter from its companion star. Its gravity draws a stream of gas, which swirls into an accretion disk before falling onto its surface. Year after year, the white dwarf's mass grows. As it approaches the 1.44 solar mass limit, its fate is sealed. The internal pressure and density climb to unimaginable levels. Suddenly, the carbon and oxygen at its core, the inert ash of a dead star, reignite. What follows is a runaway thermonuclear explosion. In seconds, a wave of fusion tears through the star, consuming it completely. The energy released is so colossal it blows the white dwarf apart, leaving nothing behind. This is a *type Ia supernova. For a few weeks, this single exploding star can outshine an entire galaxy. These explosions are more than just cosmic events. They are one of the most important tools in cosmology. Because they all happen at the exact same mass, they all have nearly the same intrinsic brightness. This makes them standard candles. By observing how bright a type Ia supernova appears, astronomers can calculate its distance with incredible precision. It was by measuring these distances that astronomers discovered that the expansion of the universe is accelerating, driven by a mysterious force we now call dark energy. The ghosts of dead stars became lighthouses, allowing us to map the cosmos and probe its deepest secrets. From the fiery heart of a living star to the cold, crystallized tomb of a black dwarf, the journey of a sun-like star is a story on a cosmic scale. At its center is the white dwarf, an object held in balance by the quiet, strange rules of the quantum world. It is a testament to the conflict between two fundamental forces: gravity, the architect of galaxies, relentlessly pulling everything together, and the quantum exclusion principle, the rule of individuality, ensuring that matter cannot be crushed into oblivion. A single teaspoon of this material, weighing more than an elephant, is more than just an unusual fact. It is a physical manifestation of this cosmic tension. It represents the point where familiar physics gives way to the quantum realm, creating an object of impossible density. And in its final, explosive moments, it can become a beacon, lighting up the universe and revealing its history. The sky above us is a laboratory where the most extreme conditions imaginable play out over billions of years. And in the heart of a dead star, we find a story about the fundamental nature of reality itself, a story of conflict, of resistance, and of a strange and beautiful equilibrium on the very edge of existence. The weirdest pressure in the universe. In the universe we know, pressure is almost always a story of heat and motion. It is born in fiery collisions, in the frantic movement of countless particles. And yet, one of the most powerful pressures in the cosmos has nothing to do with heat at all. It is a force that exists even at absolute zero, a quiet but immense resistance born from the fundamental rules of the quantum world. This is the pressure that supports the impossibly dense remnants of dead stars, preventing their final collapse for trillions of years. To understand it, we must first set aside our everyday experience and look at the normal world of pressure, just to appreciate how spectacularly the universe can operate on a different set of rules. We live our lives surrounded by pressure. It is the reason a balloon inflates and the reason the wind blows. In nearly every case, pressure is about particles crashing into their surroundings. In a simple box of gas, countless atoms zip around randomly, and every one of these collisions exerts a tiny push. The sum of these pushes, happening every moment, creates a steady force. That is thermal pressure, and it is directly tied to temperature. If you heat the gas, its particles move faster, they collide with more force, and the pressure goes up. If you cool the gas down to absolute zero, all this thermal motion, in a classical sense, would stop. The collisions would cease, and the thermal pressure would vanish. This is the intuitive world. A star like our Sun exists in a delicate balance built on this very principle. For billions of years, the relentless inward pull of gravity is perfectly countered by an outward push. This push comes from the star's core, a thermonuclear furnace where hydrogen fuses into helium, releasing a staggering amount of energy. This energy, in the form of photons, pushes outward, heating the surrounding gas and creating the thermal pressure that holds the star up. Gravity pulls in, thermal pressure pushes out. As long as the star has fuel, it remains stable. And yet, this stability depends entirely on a finite supply of fuel. And when that fuel runs out, the familiar rules begin to give way to something else entirely. For a star like our Sun, the end begins when the hydrogen in its core is exhausted. The furnace flickers, and the outward thermal pressure weakens. Gravity, ever present, begins to win. The core contracts, and as it does, the pressure and temperature in the layers around it increase until hydrogen begins to fuse in a shell. This new burst of energy causes the star's outer layers to bloat, expanding into a red giant. Inside, the core continues to shrink and heat until it becomes so dense that a new reaction begins, fusing helium into carbon and oxygen. The star has found a temporary reprieve, a new source of thermal pressure to fight against gravity. This stage, however, is fleeting. Helium burns far hotter and faster than hydrogen, and within a few million years, it too is gone. The core is now inert carbon and oxygen. For a star of this mass, there is not enough gravitational pressure to ignite carbon fusion. The fire is out for good. With no more thermal pressure pushing out from the center, nothing seems to stand in the way of gravity. The star's outer layers drift away, forming a planetary nebula, leaving the bare core behind. This core, containing about half the Sun's original mass, begins to collapse under its own weight. Classical physics suggests this collapse should be unstoppable, crushing the core into a singularity. But it doesn't. As the core is squeezed down to the size of the Earth, the collapse simply stops. It settles into its final form, a white dwarf. It is one of the densest objects in the universe. A single teaspoon of its material would weigh over 5 tons. It is also an object that is slowly cooling, radiating its leftover heat into space. This presented a profound puzzle. The star is cooling, so its thermal pressure should be decreasing, allowing gravity to crush it further. And yet, it is stable. The force supporting a white dwarf has nothing to do with temperature. To find its source, we must leave the world of stars and enter the strange, probabilistic realm of the quantum. In the quantum world, particles are also waves, and their properties are governed by fundamental limits. It is here we find the origin of our weird pressure, arising from two foundational principles. The first is the Heisenberg uncertainty principle. This principle states that there is a fundamental trade-off in how precisely you can know certain pairs of a particle's properties. The more precisely you know its position, the less precisely you can know its momentum. When you confine a particle like an electron to a smaller and smaller space, you are forcing its momentum to become more uncertain and, on average, higher. Squeezing a particle makes its kinetic energy go up, not because of heat, but because the universe demands it. This provides a small pushback, but it is not enough to stop a collapsing star. For that, we need a second, more powerful rule. This is the Pauli Exclusion Principle. Formulated by Wolfgang Pauli in 1925, it states that no two identical fermions can occupy the same quantum state at the same time. Fermions are the particles that make up matter, electrons, protons, and neutrons. A quantum state is like a particle's unique address, a complete description of its properties, including its energy and its spin. This principle is, quite literally, the reason matter takes up space. It is why electrons in an atom fill up successive energy levels, or shells, rather than all collapsing into the lowest energy state. It is the reason you cannot walk through a wall. The electrons in your body are forbidden from sharing the same state as the electrons in the wall. To see how this creates pressure, imagine an auditorium with seats arranged in rows of increasing height, representing energy levels. Electrons, like a lazy crowd, want to fill the lowest energy seats first. Once the two seats in the lowest level are filled, one for a spin-up electron, one for spin-down, that level is full. The next electrons that arrive are forced, by the exclusion principle, to occupy the next row up, a higher energy level. As more and more electrons are added, they are compelled to fill higher and higher energy states. Now, imagine the walls of this auditorium closing in, squeezing everyone together. The rows of seats themselves are pushed upward. The lowest possible energy state is now at a higher energy than before. Every single electron is forced into a higher energy state, which means it has more momentum. These increasingly energetic electrons, moving at high speeds simply because there are no lower energy states available, create a powerful outward push. This is electron degeneracy pressure. It has nothing to do with temperature. It is a purely quantum effect, a pressure that will exist even at absolute zero, born from the sheer crowdedness of matter. Returning to our collapsing star, gravity is squeezing a colossal number of electrons into a shrinking volume. The atoms are crushed to the point where the electrons are no longer tied to any single nucleus. They form a freely moving gas, flowing through a fixed lattice of carbon and oxygen ions. This is electron degenerate matter, and its density is staggering, around 1,000,000 grams per cc. This is where the quantum rules take over on a cosmic scale. As gravity tries to crush this material further, all the lowest energy states for the electrons are instantly filled. To obey the Pauli Exclusion Principle, other electrons are forced into incredibly high energy states, moving at significant fractions of the speed of light. These hypervelocity electrons generate an immense, outward pushing pressure. This is the force that halts the collapse and stabilizes the white dwarf. Unlike thermal pressure, which would fade as the star cools, degeneracy pressure is independent of temperature. It depends only on density. This creates one of the more unusual relationships in astrophysics. The more massive a white dwarf is, the smaller it is. Adding mass increases gravity's pull, squeezing the star into a smaller volume. This increased density forces the electrons into even higher energy states, generating the stronger pressure needed for a new, smaller equilibrium. We have seen these objects. The first discovered was Sirius B, the faint companion to the brightest star in our night sky. Its existence, a sun's worth of mass in a volume smaller than the Earth, was a deep mystery until the 1920s, when physicists realized electron degeneracy pressure was the only possible explanation. A white dwarf is a stellar corpse, its final collapse held in check by a quantum principle. It no longer generates new energy. It simply sits in space, a crystalline remnant that will radiate its heat away over trillions of years, far longer than the current age of the universe, eventually becoming a cold, dark object known as a black dwarf, still held up by this same quiet, persistent pressure. Electron degeneracy pressure is immense, but it is not infinite. As more mass is added to a white dwarf, often by pulling material from a nearby companion star, gravity tightens its grip. The star shrinks, and the electrons are forced to move faster and faster. As their velocities approach the speed of light, however, Einstein's theory of relativity becomes important. Adding more energy to a near-light speed particle doesn't make it much faster, it mostly adds to its inertia. This causes the pressure to increase with density less steeply than before. The resistance weakens. The astrophysicist Subrahmanyan Chandrasekhar, in 1930, calculated the consequences. He discovered there is an absolute maximum mass that electron degeneracy pressure can support. If a white dwarf's mass exceeds this limit, the pressure will fail. This threshold, the Chandrasekhar limit is approximately 1.44 times the mass of our Sun. It is one of the most important numbers in astrophysics. A white dwarf that remains below this limit will cool for eons. But one that crosses the limit, often by accretion, is destined for a violent end. As the degeneracy pressure fails, the core collapses catastrophically in a fraction of a second. This collapse triggers a runaway thermonuclear reaction that detonates the entire star in a vast explosion known as a Type Ia supernova. For stars born much more massive than our Sun, their cores are already over the Chandrasekhar limit when the furnace goes out. Their collapse is not even temporarily halted by electron degeneracy. Instead, the crush is so intense that electrons are forced into protons, forming neutrons. The collapse is then stopped by a new, even stronger version of the same phenomenon, neutron degeneracy pressure. This creates a neutron star, an object so dense a teaspoon of its material would weigh 1 billion tons. But if the core is more massive than about 3 solar masses, even this force is not enough. Nothing in the known universe can stop the collapse. The star forms a black hole. The Chandrasekhar limit is the fork in the road, the line that separates a quiet, unending afterlife from a violent, explosive one. We began with the familiar pressure of colliding particles, the force that keeps our Sun stable. We followed a star to its death, where that thermal engine goes quiet and gravity reasserts its dominance. And then, at the last moment, we saw an intervention from the deepest level of reality. A force born not from heat, but from an unbreakable quantum rule. Electron degeneracy pressure arises from the simple fact that electrons are forbidden from being in the same state at the same time. It depends not on temperature, but on crowdedness. It is the silent force that supports the corpses of stars for timescales that make the current age of the universe seem brief. It is a quiet reminder that the cosmos is governed by rules far stranger and more profound than our everyday lives might suggest. The weirdest pressure in the universe is also one of the most fundamental, ensuring that even in death, matter makes a final stand against the infinite pull of gravity. What if you dropped a teaspoon of dead star on Earth? You're in your kitchen. You reach into a drawer and pull out a teaspoon. It's an object so familiar you could hold it in the dark. But not this one. This one feels wrong. It's impossibly heavy. The metal groans, straining under a weight it was never meant to hold. Resting in the spoon is what looks like a tiny, shimmering bead. It's matter forged in the heart of a dead star, a place where the laws of physics are pushed to their absolute limit. And then, your grip slips. For a split second, the spoon and its impossible cargo just hang there. Then, it drops. What happens next? This isn't just a simple question. It's a journey into two of the most violent events the universe can create. One would destroy a city. The other would destroy the world. The universe is a place of extremes. Stars burn with unimaginable fury, and black holes devour light itself. And in the cosmic graveyards lie the silent, collapsed corpses of suns, dead stars. For our story, we care about two kinds, white dwarfs and neutron stars. Both are the super-compressed remnants of giant stars, but they represent two very different flavors of cosmic horror. You might have heard that a teaspoon of a dead star weighs as much as a mountain. But the reality is a little more complicated, and way more interesting. So, we're going to run the experiment twice. First, we'll drop a teaspoon of a white dwarf, the tamer, but still terrifying, of the two. Then, we'll swap it out for its monstrous cousin, a spoonful of a neutron star. This is a second-by-second chronicle of a catastrophe. We'll start with the white dwarf. This is what's left behind when a star like our own Sun runs out of fuel, sheds its outer layers, and its core collapses. What remains is an Earth-sized diamond made of something called electron degenerate matter. This happens to stars that aren't massive enough to become a neutron star. When the fusion that holds a star up stops, gravity wins, and it collapses. But for these smaller stars, the collapse is stopped by a quantum rule called the Pauli Exclusion Principle. Basically, it states that no two electrons can be in the same state, which creates a powerful outward pressure. This pressure fights gravity to a standstill, leaving behind an object the size of a planet but with the mass of a sun. It's no longer a star, it's a cooling ember, held up by the strange rules of the quantum world. And it's from this bizarre object that we've magically scooped our first teaspoonful. The white dwarf scenario, an unsurvivable explosion. Okay, first things first. You aren't holding this teaspoon. The material inside it has a density of about 1,000 metric tons per cc. A regular teaspoon holds about 5 cubic centimeters. So that little bead in the spoon has a mass of around 5,000 tons. Forget an elephant. That's the weight of the Eiffel Tower's iron structure, all concentrated into something smaller than a sugar cube. Your hand, the spoon, the floor, none of them stand a chance. The moment this stuff appears, the experiment has already gone sideways. So let's pretend the spoon is made of some magical, unbreakable material, and it's held by a robotic arm. The arm lets go. The spoon doesn't flutter. It plummets. It accelerates just like any other object, but its incredible density gives it a terrifying sense of purpose. It's not just falling, it's plunging toward the center of the Earth. But here's where things get really explosive. This degenerate matter is only stable under the crushing gravity of its home star. Here on Earth, without the weight of a sun pressing down on it, that quantum electron pressure has nothing to push back against. It's like a can of soda that's been shaken for 1,000,000 years, and we just pop the top. The instant it's here, it starts to fail. The quantum pressure wins, and it wins explosively. This isn't a chemical explosion like TNT. It's a physical one. The tightly packed atomic nuclei, which were stripped of their electrons, now repel each other with unimaginable force. So, as it drops, two things happen at once. First, the impact. Even falling from a few feet, 5,000 tons hitting the floor is a disaster. It would blast a massive crater, shattering your house and every building on your street. But that's just the opening act. The main event is the decompression. Those 5 cubic centimeters of white dwarf matter expand. How much? Well, it wants to return to a normal density, something like carbon or oxygen plasma. This is a volume increase of hundreds of thousands of times, happening in less than a microsecond. The result is an explosion. Not just an explosion, a brilliant flash of light brighter than the sun, and a wave of heat that instantly vaporizes everything for blocks. The air itself is superheated into plasma, creating a fireball that expands outwards, melting asphalt and turning buildings and people into shadows and dust. A hemispherical shockwave follows, moving faster than sound, a wall of pressure that flattens structures for miles in every direction. The sound would be a single, deafening crack that ruptures eardrums for anyone who survives the initial blast. What was once a city is now a smoking, circular crater several kilometers across. At the center, there is nothing. The ground itself is gone, vaporized. Further out, a ring of total destruction where buildings are reduced to skeletal remains. Beyond that, a zone of severe damage with every window shattered and fires raging everywhere, ignited by the intense pulse of heat. The aftermath is a nightmare. A colossal mushroom cloud of vaporized earth and debris rises into the stratosphere, casting a dark, toxic shadow. The fallout isn't traditionally radioactive, but a poisonous dust of exotic matter that will contaminate the region for decades. It would be an event on the scale of a large nuclear detonation. Scientists would be baffled. Seismic sensors would register a massive explosion, but there'd be no telltale isotopes of a nuclear bomb. It would be a new type of catastrophe, a city killer born from the laws of physics. Humanity would survive. The planet would be scarred, a city wiped off the map, but it would be a localized, though horrific, disaster. A terrifying warning from the cosmos. But that was the white dwarf. That was the tame one. An entire city, gone in the blink of an eye. A disaster on a scale we can barely imagine, all from something smaller than a marble. And as terrifying as that was, it was just a firecracker. Now, it's time to light the dynamite. Before we run this experiment again with the most extreme substance in the known universe, take a second to subscribe and hit that notification bell. You won't want to miss what happens when we swap out the contents of our spoon for a real monster. The neutron star scenario. A planet-killing event. We're back in the kitchen. The same unbreakable spoon is held by the same robotic arm. But the bead inside it is different. It's darker, seeming to swallow the light around it. It feels like it's warping the very air it sits in. This isn't white dwarf matter. This is neutronium, the stuff of a neutron star. If a white dwarf is the corpse of a sun-like star, a neutron star is the ghost of a true giant. When a really massive star dies, gravity overwhelms everything. Electrons and protons are crushed together to form neutrons. The entire star, with more mass than our sun, collapses into a ball no wider than a city, maybe 20 kilometers across. The only thing stopping it from becoming a black hole is a new quantum force, neutron degeneracy pressure. This is what happens when you pack fundamental particles as tightly as physics allows. All the empty space in an atom is just gone. What's left is a solid ball of pure nuclear matter. The density is no longer 1,000 tons per cc. For neutron star matter, a single teaspoon doesn't weigh 5,000 tons. It weighs 10 billion kilograms. 10 million tons. Let that sink in. 10 million tons. That's the weight of the Great Pyramid of Giza, times 2. It's the weight of the entire human population, packed into a teaspoon. So, what happens when we drop it? The question itself is wrong. The moment this teaspoon of neutronium appears on Earth, dropping is irrelevant. Its own gravity is so powerful, it makes the rules. The robotic arm holding it isn't crushed, it's annihilated. Its atoms are ripped apart by tidal forces and stream into the neutronium. The floor, the building, the air, they don't fall. They flow towards the teaspoon as if it were a microscopic black hole. A deafening, continuous roar fills the space as the atmosphere rushes into the vacuum being created. The neutronium doesn't hit the ground. It consumes it. It starts its journey to the center of the Earth, punching through the crust as if it were a soap bubble. The rock in its path isn't pushed aside. It's super compressed and vaporized by the pressure, leaving a channel of incandescent plasma behind it. This isn't a slow fall. It passes through the crust, dozens of kilometers, in a fraction of a second. It plunges into the mantle, the thick layer of molten rock that makes up our planet. To the neutronium, the syrupy mantle is like empty space. It just keeps falling, accelerating towards the core. The path it carves is a tunnel of pure chaos. This sudden vaporization of mass triggers a seismic wave of unimaginable power. This isn't an earthquake. This is a planetary convulsion. The entire crust of the Earth rings like a bell. Fault lines all over the globe rupture at once. Cities aren't just shaken, they're torn apart as the ground beneath them rips itself to pieces. But the journey's not over. The neutronium reaches the center of the Earth. It doesn't stop. Its momentum is too great. It overshoots the core and continues, now, falling, up towards the other side of the planet. It bursts through the surface on the opposite side of the world, somewhere in the Indian Ocean, in a cataclysmic explosion of vaporized mantle and core material that gets ejected thousands of kilometers into space. The resulting tsunami isn't a wave, it's a wall of boiling water kilometers high that scours continents clean. And it's still not over. After exiting the Earth, it's pulled back by our planet's gravity. It slows, stops, and falls back, re-entering through the hole it just made and starting the journey all over again. It has become a needle of destruction, oscillating back and forth through the heart of our world. Each pass deposits more energy into the planet's interior. The Earth's core is repeatedly punctured and superheated. The mantle is churned into a chaotic soup. On the surface, it's the apocalypse. The seismic shocks shatter the tectonic plates. Supervolcanoes erupt on every continent at once. Fissures miles deep tear open, venting molten rock and poison gas from the mantle. The sky turns black with ash, blotting out the sun, lit only by the hellish red glow of a planet cracking open. The oceans boil away. The atmosphere is stripped into space. Within hours, Earth is no longer a blue marble. It's a glowing, molten sphere of lava. The oscillating neutronium eventually settles in the core, but by then, there is no Earth left. What remains is a new asteroid belt, a tombstone of debris orbiting the Sun where a world used to be. The cosmic perspective. We've just witnessed the end of the world. A tiny pellet of stable neutron star matter tunneling through our planet. But in chasing this gravitational horror story, we've missed the real punchline. Just like the white dwarf matter, neutronium is not stable without the crushing gravity of its parent star. In a neutron star, gravity is so intense it prevents neutrons from decaying. But free neutrons are unstable. With a half-life of about 10 to 15 minutes, a lone neutron decays into a proton, an electron, and an antineutrino, releasing energy. The moment our teaspoon of neutronium appears on Earth, it's no longer under that stabilizing pressure. All 10 million tons of neutrons begin to decay. All of them, all at once. This is an explosion that dwarfs everything we've just discussed. The energy released by this decay is staggering, comparable to the total energy our Sun puts out over several seconds. So, what really happens when you drop a teaspoon of a neutron star? There is no descent, no tunnel, no oscillation. The instant the neutronium appears, it detonates. It's an explosion so vast the word feels meaningless. The energy release would be millions of times greater than the asteroid impact that wiped out the dinosaurs. Everything within hundreds of kilometers is instantly vaporized. The Earth's crust is peeled back like an orange, and a huge portion of the planet's mantle is ejected into space. A wave of radiation, gamma rays and X-rays, flashes outwards at the speed of light, sterilizing the moon on its way past. The planet is cracked to its core and shattered into molten fragments. Our world ceases to exist in a single, silent flash of light. There would be no scream, no final moment of terror. The end would come and go faster than a thought. The thought experiment itself is its own undoing. The material is so extreme, so alien, that it cannot exist here without immediately and violently exploding. The only conditions that can create it are the only conditions that can contain it. This journey, from a city-ending blast to a planet-shattering detonation, reveals a fundamental truth. We exist in a calm, gentle oasis, protected by the vast, empty distances between stars. Out there, in the dark, are forces on a scale we can't truly comprehend. White dwarfs and neutron stars aren't just monsters in a story, they are real. There are billions of them in our galaxy. Our existence is a delicate balance. This terrifying fantasy is a profound reminder of the raw power of the universe, and the incredible fragility of everything we have ever known. So, what if you dropped a teaspoon of a dead star on Earth? If it's from a white dwarf, you get an explosion that erases a city, a quantum catastrophe that leaves a permanent scar on our world. But if that teaspoon is from a neutron star, the story is much, much shorter. There is no story. The experiment ends the instant it begins, in a detonation that unmakes the world, tearing our planet apart in a single, silent, brilliant flash. We've seen how matter can be compressed into states so dense and energetic it breaks our minds. The universe, in its stellar graveyards, contains horrors and wonders beyond our wildest imagination. And while we'll never hold a piece of a dead star, knowing that such things are out there forever changes how we see our small, safe, and precious home in the cosmos. The cosmic paradox: why adding mass makes these stars shrink. In the vast, silent theater of the cosmos, we rely on a few simple rules. Physical laws from our everyday lives, scaled up to the heavens. They give a sense of order, a logic to the grand design. One of the most basic is this: add more matter, and something gets bigger. A planet gathers mass, its diameter expands. A star, born from a collapsing cloud, swells as it accumulates dust and gas. This is the universe as we expect it to be. But this rule is not universal. In the ghostly graveyards of the cosmos, there are stellar corpses that defy this logic. Objects so strange, they operate under different principles. For these stars, a profound secret, a cosmic paradox, turns our intuition on its head. The more mass you add to them, the smaller they get. This is not theory. It is an observed reality of our universe. A truth found not in the familiar world of gravity and heat, but deep within the bizarre realm of quantum mechanics. A place where a fundamental law of individuality prevents these dead stars from collapsing, forcing them into an impossible state of being. This is the story of that quantum refusal, and the cosmic paradox that makes these stars shrink. Before we see the exception, we must understand the rule. The physics of our everyday lives. When you build anything, the principle is self-evident. You add more material, the object grows. This intuition is deeply ingrained. Now, we scale this up to the cosmic level. A star, like our Sun, begins in a vast, cold nursery. A molecular cloud of hydrogen and dust. It stretches for light years. It drifts. Then, something disturbs it. A shockwave, a gravitational nudge, a pocket of slightly higher density forms. Once that seed exists, gravity takes over. It is a force of accumulation. It pulls matter together. The pocket of gas begins to contract, pulling in more and more material. As the core gets denser, something else happens. It gets hotter. Gas particles, squeezed together, collide. This generates thermal pressure, an outward push. For a long time, the new star is in a battle with itself. Gravity tries to crush it. Thermal pressure pushes back, but gravity keeps winning. For a time, the star continues to grow, in mass and in size. Eventually, the core becomes so extreme, nuclear fusion ignites. Hydrogen atoms fuse to form helium, releasing a tremendous amount of energy. A star is born. Now, the star enters a stable period. The main sequence. Here, the outward push of fusion is balanced with the inward pull of gravity. And for these living stars, the rule holds. More massive stars are bigger. More mass means more gravity. To counteract that crush, the star needs more thermal pressure. The only way is to increase the rate of fusion. A hotter core puffs up the star's outer layers. So, for the vast majority of stars, mass and size are directly related. This logic applies to planets, moons, and almost everything we see. The universe seems to follow this one simple law. Except, when it doesn't. To find the exceptions, we must leave the stellar nurseries and travel forward in time, to the end of a star's life, to the stellar graveyard, where the laws of quantum mechanics overthrow the familiar rules, and where the cosmic paradox awaits. All stars must die. Their lives are a long battle against gravity, fought with the fire of fusion. But the fuel is finite. When it runs out, gravity claims its victory. The final corpse a star leaves behind depends on its initial mass. Consider stars like our Sun. In about 5 billion years, the hydrogen in its core will be gone. The furnace will sputter. Gravity will start to compress the core. This compression ignites a new phase. Hydrogen begins to fuse in a shell around the inert core. This phase is intense. The energy pushes the star's outer layers outward. The Sun will swell into a red giant, hundreds of times its current size. A vast, bloated, crimson orb. This is temporary. Eventually, the helium core itself will ignite, fusing into carbon and oxygen. But for a star of the Sun's mass, this is the end. It does not have enough gravity to fuse carbon and oxygen. The fusion engine dies. The star's outward pressure vanishes. Its outer layers drift away into space. A beautiful, glowing shroud. A planetary nebula. The star's final breath. What is left is the star's heart. A naked core of carbon and oxygen. This is a white dwarf. It no longer produces energy. Just an ember, glowing with leftover heat. Destined to cool for trillions of years. Until it becomes a cold, dark black dwarf. But what of stars much more massive than our Sun? Their lives are spectacular. Their deaths, cataclysmic. They burn through their fuel at a ferocious rate. When their fuel runs out, they swell into red supergiants. Their cores are massive enough to continue fusion. Helium to carbon, carbon to neon, oxygen to silicon, and finally, silicon to iron. The core becomes layered. Like an onion, iron is the ultimate stellar ash. Its fusion consumes energy. It does not release it. The star's energy source is cut off. In less than a second, gravity wins. Catastrophically, the iron core collapses. This triggers a shockwave that blows the star apart. A Type II supernova. For weeks, it can outshine an entire galaxy. What remains depends on the mass of the core. If the core is between 1.4 and 3 times the mass of our Sun, protons and electrons are crushed together. They form a sea of pure neutrons. A neutron star. If the core is more massive, nothing can stop its collapse. It collapses indefinitely, into an infinitely small point. A singularity, tearing a hole in the fabric of spacetime, creating a black hole. So the stellar graveyard is populated by these 3 remnants. White dwarfs, neutron stars, black holes. These are the rule breakers. They have no fire to hold them up. They are supported by a different, stranger force. And in the white dwarfs and neutron stars, we find our cosmic paradox. Let's focus on the most common of these stellar corpses. The white dwarf. The fate that awaits over 97% of the stars that will end their lives in our galaxy. Including our own Sun, a star's worth of matter. Packed into a planet-sized volume. The density is almost beyond comprehension. A single teaspoon of its material would weigh as much as an elephant. They are born incredibly hot, shining with a brilliant, white light. But this light is not from fusion. It is residual heat, like iron pulled from a forge. Recent discoveries have shown that as they cool, the carbon and oxygen in their cores are predicted to crystallize, essentially turning them into galaxy-sized diamonds. One of the first to be discovered was Sirius B. The brightest star in our sky, Sirius, is a binary. It has a tiny, faint companion. Predicted in 1844, because of a wobble in the main star's motion. It was being tugged by an unseen object. When finally seen, astronomers were baffled. This tiny companion had a mass equal to our Sun, but it was incredibly faint. The only way for it to be so massive, yet so dim, was if it was incredibly small. A stellar heavyweight, in a planetary-sized package. This incredible density poses a question. A living star is held up by thermal pressure. A white dwarf has no fusion. So, what stops gravity from crushing it even further? Something is pushing back. Here, classical physics fails. The answer came from a new understanding of matter. Quantum mechanics. The force holding up a white dwarf is a purely quantum phenomenon. It is called electron degeneracy pressure. And understanding this ghostly, powerful force is the key to unlocking the paradox. To understand, we must go deeper. Into the fabric of matter itself. The quantum realm. In quantum mechanics, electrons are not tiny balls. They are like ghostly clouds of probability. In specific energy levels, an atom is almost entirely empty space. The solidity of matter comes from the refusal of these electron clouds to overlap. This brings us to a fundamental rule. The Pauli Exclusion Principle. It states that no 2 identical fermions, like electrons, can occupy the same quantum state simultaneously. Think of it like a cosmic hall, with an infinite number of unique, assigned seats. The electrons are the audience. The exclusion principle is the rule. 1 electron per seat, no exceptions. They are fundamentally individualistic. In a normal gas, there are plenty of available seats. But in the core of a dying star, it is different. Gravity is crushing matter to an unimaginable degree, creating a super-dense soup of nuclei and free electrons. Gravity tries to force all these electrons into the lowest possible energy states. And here, the Pauli Exclusion Principle stages a quiet refusal. It says, no, the lowest energy seats fill up. When a new electron is forced in, it cannot occupy a filled low energy state. It is forced to occupy a higher energy level. It must move with a higher speed. As gravity crushes the core, more electrons are forced into progressively higher energy states. Moving faster and faster, these high-energy electrons create a powerful, outward pressure. This is electron degeneracy pressure. And this pressure has almost nothing to do with temperature. In a degenerate gas, even at absolute zero, the electrons would still be forced into high-energy states. The pressure would remain. A pressure born not from heat, but from a quantum rule that matter refuses to lose its individuality. This is the force that holds up a white dwarf. And it is the source of the paradox. We have now arrived at the heart of the paradox. A white dwarf. A balance of forces. The inward crush of gravity. The outward push of electron degeneracy pressure. Now, we add more mass to our white dwarf. Our intuition says the star should get bigger. But let's follow the quantum logic. When we add mass, we increase gravity. The inward crush intensifies. The electron degeneracy pressure must now increase to fight this stronger pull. But this pressure is not thermal. The only way to increase it is to force the electrons into even higher energy states. To do this, gravity must squeeze the star more tightly. By compressing the star into a smaller volume, electrons are forced closer together. They populate more energetic levels, moving at even more frantic speeds. This boosts the degeneracy pressure. The star settles into a new equilibrium. Gravity is stronger. Degeneracy pressure has matched it. But to achieve this new balance, the star had to become smaller. Its radius had to shrink. This is the cosmic paradox. Adding mass increases gravity, which compresses the star, which increases the density, which boosts the degeneracy pressure, resulting in a new equilibrium at a smaller size. It is a counterintuitive feedback loop, governed by the strange laws of the quantum world. Observations have confirmed this prediction. Data from thousands of white dwarfs shows a clear curve. The more massive the white dwarf, the smaller its radius. This is why these stars break our common sense rules. Our intuition is built on thermal pressure. For a white dwarf, the pressure source is quantum and density dependent. The only way it can fight back against more gravity is to become denser. The only way to become denser is to shrink. But this quantum refusal has a limit. In 1930, on a journey from India to England, the 19-year-old astrophysicist Subramanian Chandrasekhar made a discovery that would change our understanding of stars. He combined quantum mechanics with Einstein's special relativity. He realized that as you add mass to a white dwarf, it shrinks, and its electrons move faster. Eventually, they approach the speed of light. Here, relativity changes things. It becomes harder and harder to accelerate a particle as it nears light speed. For the degenerate electrons, this means they can't increase their pressure as effectively as before. The degeneracy pressure becomes softer. Chandrasekhar calculated the exact point of disaster. An absolute upper limit to the mass that electron degeneracy pressure can support. This is the Chandrasekhar limit. For an idealized, non-rotating white dwarf, its value is approximately 1.44 times the mass of our Sun. A white dwarf below this limit is stable. But a white dwarf that acquires enough mass to cross it is doomed. Degeneracy pressure fails. The star begins to collapse again. What happens next is one of two possibilities. In a binary system, a white dwarf pulls matter from a companion. As it nears the 1.44 solar mass limit, the temperature and pressure in its core skyrocket. The carbon and oxygen ignite in a runaway thermonuclear reaction. In a matter of seconds, the entire star undergoes explosive fusion. The result is a Type Ia supernova, an explosion that completely obliterates the white dwarf. These explosions are so consistently bright, astronomers use them as standard candles to measure the vast distances across the universe. There is another, quieter possibility. If the white dwarf is made of heavier elements, it may not explode. Instead, as it crosses the limit, the collapse continues. The pressure becomes so great that electrons are forced inside atomic nuclei, combining with protons to form neutrons. This process is called electron capture. The very particles that provided support vanish. The star collapses catastrophically, from the size of the Earth to the size of a city. In less than a second. This collapse is halted only when the new neutrons themselves become degenerate, creating neutron degeneracy pressure. The star has become a neutron star. A neutron star is the paradox taken to its extreme. Up to 3 times the mass of the Sun, crushed into a sphere no larger than a city. A single sugar cube of its material would have the same mass as all of humanity. Gravity on its surface is billions of times stronger than Earth's. They are born spinning hundreds of times per second. Like white dwarfs, they are held up by degeneracy pressure. But this time, it is the neutrons. The principle is the same. The Pauli Exclusion Principle forbids 2 neutrons from occupying the same quantum state. This generates an immense outward pressure. And the paradox remains. Add mass to a neutron star, and its gravity increases. To fight back, the pressure must increase. The star must compress further and shrink into an even smaller, denser ball. More massive neutron stars are smaller than less massive ones. This, too, has a limit, known as the Tolman-Oppenheimer-Volkoff limit, somewhere between 2 and 3 solar masses. If a neutron star crosses this limit, no known force can stop its final collapse. It will become what lies at the very end of the line. A black hole. The journey into the heart of a white dwarf has taken us from the common sense rules of our world to the alien landscape of the quantum realm. We started with a simple idea, that adding more stuff makes things bigger. And we watched the universe dismantle that idea in the stellar graveyard. The shrunken remnants of stars are not held up by fire, but by a strange quantum law. A principle of individuality that gives rise to electron degeneracy pressure. A force born not from heat, but from reality itself. It is this pressure that creates the paradox. In its fight against gravity, a white dwarf has no choice but to shrink as it gains mass. This is a fundamental feature of the universe. A testament to the fact that reality operates under different rules at different scales. We saw how this paradoxical dance has a final, dramatic end. The Chandrasekhar limit, a point of annihilation or transformation into an even more extreme object. A neutron star, which continues the same paradox on a denser scale. These shrinking stars are more than curiosities. They are laboratories for extreme physics. They are the origin of the supernovae that allow us to measure the cosmos. And they are a glimpse into the far future. A vision of what our own sun will become. The universe, it turns out, is not always intuitive. Its deepest truths often lie hidden in paradoxes. In the places where our common sense fails. The story of the shrinking star is a reminder that there is a vast and wonderfully strange reality just beneath the surface of what we see. And that the cosmos will always find new ways to astonish us. The cosmic tipping point that erases stars. Long before our world took its familiar shape, the stars were already there, fixed points of light in a quiet, unchanging sky. That quiet is an illusion. The universe is not a place of permanence but of transformation. Stars are born, live, and die in cycles that span billions of years. And the fate of every star, Whether it fades gently or is erased in a flash of light, is decided by a single, invisible line. This is a journey into that invisible line. It begins in the summer of 1930, on a steamship crossing the Indian Ocean. A 19-year-old physicist named Subramanian Chandrasekhar was traveling from his home in India to Cambridge University. The journey took weeks. There was no internet, no phone, only books, paper, and his own thoughts. On that long voyage, a question began to form. What happens when a star dies? The accepted answer was that they simply fade. For Chandrasekhar, that explanation was incomplete. And so, with a pencil and notebook, he began to calculate. He did not set out to challenge the world's most famous astronomer. He was simply following the math. But his calculations revealed a universal limit for the dead, a number that determines if a star's story ends, or is violently rewritten. To understand the journey that led to this discovery, we first need to understand the life of a star. Every star, including our own sun, exists in a state of delicate balance. It is a balance between two fundamental forces. On one side is gravity, the immense, relentless force that pulls every atom of the star inward, attempting to compress it into the smallest possible point. Opposing this inward pull is the outward pressure created by nuclear fusion. Deep in the star's core, the heat and pressure are so extreme that hydrogen atoms are fused into helium. This process releases a tremendous amount of energy as light and heat, creating a thermal pressure that pushes outward. For most of a star's life, these two forces are in equilibrium. Gravity pulls in, fusion pushes out. This stable period is called the main sequence. Our sun is in this state now and will be for another 5 billion years. But the fuel for fusion is not infinite. A star's mass is its most important trait, deciding its temperature, brightness, and its end. Stars range from small red dwarfs that burn for trillions of years, to massive blue supergiants that live for only a few million. The story of their death, and the tipping point Chandrasekhar found, begins when their fuel runs out. When a star exhausts the hydrogen in its core, the balance between gravity and pressure is broken. The core contracts, increasing its temperature and pressure until helium begins to fuse into carbon and oxygen. This new release of energy pushes the star's outer layers outward. The star expands and cools, becoming what is known as a red giant. Our own sun will one day enter this phase, swelling to engulf the inner planets. But this, too, is temporary. For a low to medium mass star like the sun, there is not enough gravitational pressure to ignite the carbon and oxygen core. The fusion engine stops. The star then sheds its outer layers into space. These expanding shells of gas are lit by the hot core, creating objects we call planetary nebulae. What remains is a small, extremely dense core, a white dwarf. This is the final state for more than 97% of all stars. A quiet end. For the most massive stars, however, a different fate awaits. They are heavy enough to continue fusing elements until they reach iron. Fusing iron does not release energy, it consumes it. When the core of a massive star becomes iron, its power source fails catastrophically. What follows is not a gentle fade, but a supernova. There were two known endings: a quiet retirement as a white dwarf or a violent explosion. But no one knew where the line was drawn. The answer would be found not in an observatory, but in the mind of a young man crossing an ocean. Before we follow Chandrasekhar on his voyage, we need to understand what a white dwarf is. It is the exposed core of a dead star, an ember glowing with leftover heat. The most remarkable quality of a white dwarf is its density. A mass comparable to our sun is crushed into a volume the size of the Earth. A single teaspoon of its material would weigh as much as an elephant. The atoms are packed so tightly they enter a state called degenerate matter. With no fusion pushing outward, what stops gravity from crushing it further? The answer is not heat. It is a quantum mechanical effect known as electron degeneracy pressure. To understand this, we need to look at a rule called the Pauli Exclusion Principle. This principle states that no two electrons can occupy the same quantum state at the same time. You can think of it like assigned seating. Each electron has its own seat and cannot move into one that is already occupied. In the hyper-compressed core of a white dwarf, all the lower energy states are filled. As gravity tries to squeeze the matter tighter, it is trying to force electrons into states that are already occupied. The electrons resist. They are forced into higher energy levels, creating a powerful outward pressure that is independent of temperature. This pressure is the quantum shield that holds the star up against its own gravity. For a time, it is a stable equilibrium. But Chandrasekhar's work would show that this shield has a breaking point. Let us return to the ship sailing across the Indian Ocean in 1930. On board, Chandrasekhar was considering this problem. He knew that the stability of white dwarfs was explained by electron degeneracy pressure. But he also knew those calculations did not account for Einstein's theory of special relativity. Inside the most massive white dwarfs, electrons would be forced to move at speeds approaching the speed of light. And at those speeds, relativity changes things. His goal on the voyage was to combine quantum mechanics with special relativity. No one had done it successfully. Day after day, he filled his notebooks with equations. As he worked, a pattern began to emerge. In the non-relativistic model, degeneracy pressure always increases enough to counteract gravity. The star simply becomes smaller and denser as mass is added, but it remains stable. When Chandrasekhar included relativity, this changed. He found that as electrons approach the speed of light, their behavior is altered. The pressure they exert no longer increases at a sufficient rate to counter gravity. Its effectiveness begins to level off. The quantum shield weakens. His equations showed there was a specific, critical mass beyond which gravity would always win. Above this mass, nothing in the known laws of physics could stop the star from collapsing completely. By the time his ship arrived in England, he had found the cosmic tipping point. The number is now known as the Chandrasekhar limit. It is approximately 1.44 times the mass of our Sun. A stellar core with a mass below this limit will become a stable white dwarf and slowly cool over trillions of years. A core with a mass above this limit is destined for collapse. The mathematics behind this are subtle. The relationship between pressure and density changes as electrons become relativistic. This small mathematical shift has monumental consequences. It creates an instability where, above a certain mass, the structure is guaranteed to collapse. Armed with this discovery, the young Chandrasekhar arrived at Cambridge, ready to share his findings. His work came to the attention of Sir Arthur Eddington, a leading figure in astronomy who had famously confirmed Einstein's theory of general relativity. In January 1935, Chandrasekhar was invited to present his work at a meeting of the Royal Astronomical Society. He laid out his calculations and his conclusion, that a star above a certain mass must collapse. What happened next was unexpected. Eddington took the stage and dismissed the finding as absurd. He did not engage with the mathematics. He simply rejected the conclusion, stating, "I think there should be a law of nature to prevent a star from behaving in this absurd way." The attack was public and thorough. In that moment, the scientific establishment sided with its famous leader. No one spoke in defense of the young physicist from India. For years, Eddington used his influence to oppose the idea. This had a profound effect on Chandrasekhar. He left the United Kingdom for the United States and shifted his research to other areas of astrophysics. Historians still debate Eddington's motivations. Part of it may have been a genuine inability to accept the strange implications of the math, the collapse into what we now call a black hole. But the context of the era is also noted, with a young colonial subject challenging the established scientific order. Regardless of the reason, Chandrasekhar knew his mathematics were correct. And truth in science, like gravity, cannot be suppressed indefinitely. While the scientific community debated, the universe continued to follow the law Chandrasekhar had uncovered. The 1.4 solar mass limit is an active dividing line. Crossing it leads to two of the most powerful events in the cosmos. The first path involves a single, massive star, one born with more than about 8 times the mass of our Sun. These stars fuse progressively heavier elements in their cores, ending with iron. Fusing iron consumes energy, so the star's internal engine shuts down. The iron core, supported only by electron degeneracy pressure, quickly grows beyond 1.4 solar masses. It crosses the limit. The core collapses in a fraction of a second. Protons and electrons are forced together to form neutrons, creating a new, ultra-dense object, a neutron star. This new core is supported by neutron degeneracy pressure. The outer layers of the star, falling inward, rebound off this unyielding surface in a massive shockwave. The star is torn apart in what is known as a type 2, or core collapse, supernova. If the original star is so massive that the collapsing core exceeds about 3 solar masses, even neutron degeneracy pressure fails. Nothing can stop the collapse. The core shrinks to a point of infinite density. A black hole is formed. The second path begins with a stable white dwarf in a binary system with another star. The white dwarf can pull material from its companion, slowly increasing its own mass. Over time, it approaches the Chandrasekhar limit. When its mass finally crosses the 1.4 solar mass threshold, the pressure and temperature in its core become high enough to ignite carbon fusion. Because the star is made of degenerate matter, this triggers a runaway thermonuclear reaction. In a matter of seconds, the entire star is consumed. The energy released completely overcomes the star's own gravity. The white dwarf is obliterated in an event known as a type E supernova. Unlike a core collapse event, it leaves nothing behind. Eventually, as other physicists confirmed the calculations and evidence grew, the scientific community came to accept the discovery. In 1983, Chandrasekhar was awarded the Nobel Prize in Physics for his work on the evolution of stars. Eddington had passed away decades earlier, long before the full importance of the limit was understood. Today, the Chandrasekhar limit is a fundamental tool. It tells us where to look for neutron stars and black holes. But what makes it especially important is its role in type E supernovae. Because these explosions all begin in nearly the same way, a white dwarf crossing the 1.44 solar mass limit, they have a remarkably consistent peak brightness. This makes them what astronomers call standard candles. By measuring how dim a distant type E supernova appears, we can calculate how far away it is with great precision. In the late 1990s, astronomers using these standard candles made a remarkable discovery. They found that the expansion of the universe is not slowing down, but accelerating. This discovery, which introduced the concept of dark energy, would have been impossible without the standard candles created by white dwarfs hitting the Chandrasekhar limit. The echo of a calculation on a ship in 1930 led to one of the biggest questions in modern physics. The story of the Chandrasekhar limit is a reminder that the universe is governed by laws that are often far stranger than our intuition expects. It is also a story about how science works, through quiet persistence and the gradual acceptance of new ideas. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. From the solitude of a sea voyage to a quiet vindication decades later, the discovery of this limit changed our understanding of the cosmos. It drew an invisible line in the fabric of space, separating the quiet stellar graveyard from the sites of cosmic transformation. The limit is more than a number. It is the physical law that governs the creation of neutron stars and black holes, and the thermonuclear erasure of entire worlds. It provided us with the tools to measure the universe and to find mysteries we did not know existed. Every star is on a journey, its final chapter already written in its mass. Most will fade, but for any star that crosses that critical threshold of 1.44 solar masses, a different end is set in motion. And it reminds us that some of the most profound truths can be found not in a grand discovery, but waiting patiently in the quiet space between what we know and what the numbers say must be true. The universal weight limit that destroys stars. In the universe, as on Earth, there are rules. They are not written down, but are part of the structure of space and time. Most are gentle, guiding the slow turn of a planet or the steady light of a distant star. But one rule is different. It is a quiet line, a universal weight limit that, when crossed, leads to a star's complete disassembly. This is not a theory, but a process that plays out in the final moments of a star's life. Perhaps the most interesting part of this story is not the cosmic event itself, but how it was discovered. The man who found it, a young physicist, was so unsettled by what his own mathematics were telling him that it led to one of the most significant disagreements in the history of astronomy, placing him in opposition to the most famous scientist of his time. This is the story of a point of no return, a quiet threshold that, once crossed, allows a star to erase itself in a flash of immense energy. Our story begins not in an observatory, but on the ocean. In 1930, a 19-year-old student from British India named Subramanian Chandrasekhar was on a ship, traveling to England to study at the University of Cambridge. He was familiar with the newest ideas in physics, Einstein's special relativity and the unfamiliar world of quantum mechanics. During the quiet weeks at sea, he began to think about the fate of stars. Specifically, the dense, shrunken cores left behind by stars like our Sun, known as white dwarfs. He began to write down equations, combining the physics of the very large with the physics of the very small. The mathematics were elegant, but the answer they produced was deeply unfamiliar. The equation suggested a star could become so heavy, so dense, that it would collapse under its own weight, and that nothing could stop it. It predicted a definite upper limit to how massive these stellar remnants could be. This was more than a new piece of science, it was a cosmic boundary. When he arrived in England and presented his work, his mentor, the great astrophysicist Sir Arthur Eddington, did not just disagree. He publicly dismissed the idea, famously declaring his belief that there should be a law of nature to prevent a star from behaving in this absurd way. The scientific community, respecting Eddington, largely turned away. But Chandrasekhar was right, and the absurd behavior he had uncovered would turn out to be one of the most important processes in the universe. The life of a star, a quiet balance. To understand this weight limit, we first need to understand what a star is. At its heart, every star exists in a quiet, long-lasting balance against a single, constant force. Its own gravity. Think of a star as a great sphere of gas, mostly hydrogen. Gravity is always trying to pull all of that gas inward, toward the star's center. If this pull were unopposed, a star would collapse in an instant. But something is pushing back. That something is the star's engine, nuclear fusion. Deep in the core, the immense pressure and temperature are so extreme that they cause hydrogen atoms to fuse together, creating helium. This process releases a vast amount of energy as light and heat. This outward flow of energy creates a powerful thermal pressure, a constant push from the inside out that balances gravity's inward pull. For millions or even billions of years, the star remains in this state of delicate balance, known as hydrostatic equilibrium. Gravity pulls in, and fusion pushes out. As long as there is fuel in its core, the star remains stable, shining. Our own sun has been in this balanced state for about 4.6 billion years, and has enough fuel to continue for another 5 billion. But no star has an infinite supply of fuel. Eventually, the supply begins to run low. For stars like our sun, this process begins when the hydrogen in the core is used up. When that happens, the fusion engine changes. The outward push of thermal pressure weakens, and gravity begins to win. The core starts to contract and heat up, eventually becoming hot enough to start fusing the helium it created into heavier elements, like carbon and oxygen. This new phase causes the star's outer layers to expand, turning it into a red giant. The star becomes hundreds of times larger, but this is a temporary state. Fusing helium is less efficient than fusing hydrogen, and it doesn't last as long. Eventually, the helium fuel also runs out. For a star with a mass similar to our Sun, this is the end of its fusion life. It does not have enough mass to create the pressure needed to fuse carbon and oxygen. The fusion engine stops for good. Gravity, after all this time, finally takes over. The star's long balance is over. What happens next is not a violent explosion, but a quiet end that gives rise to one of the strangest objects in the universe. The inevitable end, the birth of a white dwarf. With its nuclear engine quiet, the star can no longer support its own weight. The outer layers, which had expanded during the red giant phase, drift away into space, creating a beautiful, glowing cloud of gas called a planetary nebula. What is left behind is the star's exposed core, a hot, compact sphere of carbon and oxygen. This is a white dwarf. And compact is an understatement. A white dwarf is an object of almost unimaginable density. Imagine taking the entire mass of our Sun and crushing it down into a ball roughly the size of Earth. The material is squeezed so tightly that a single teaspoon of it would weigh several tons. The density is nearly 1,000,000 times that of water. At these pressures, the nature of matter itself changes. Gravity overcomes the usual repulsion between atoms, stripping electrons from their nuclei. The core becomes a sea of carbon and oxygen nuclei floating in a dense gas of free electrons. This is no longer normal matter. It is a state known as electron-degenerate matter. Gravity continues to crush this sphere, trying to make it even smaller. But now, a new force pushes back. It is not heat pressure, there is no fusion to generate that. This new force comes from the quantum world. It is called electron degeneracy pressure. This is a consequence of the laws of quantum mechanics, specifically a rule that states no two electrons can occupy the same state in the same space. Think of it like trying to fill seats in a room. At first, there is plenty of space. But as you add more and more people, they begin to push back against being squeezed closer together. Electrons behave in a similar way. As gravity tries to force them into a smaller volume, the electrons resist. They are forced into higher and higher energy levels, and this creates a powerful outward pressure. This pressure is astonishingly strong. It is the only thing holding the white dwarf up, preventing gravity from crushing it further. For most stars that die, this is their final, stable state. A cooling, fading ember, supported by a quantum principle. It will spend trillions of years slowly radiating away its heat until it becomes a cold, dark object, a black dwarf. A quiet monument to a star that once was. But this quantum support has a breaking point. Electron degeneracy pressure is strong, but not infinite. And this is where the equation from Chandrasekhar's sea voyage re-enters our story. The point of no return, the Chandrasekhar limit. As a young student, Subramanian Chandrasekhar understood something that others had missed. He realized that as you add more mass to a white dwarf, gravity's pull gets stronger. To counteract this, the electrons are squeezed tighter and are forced to move faster. But there is a universal speed limit, the speed of light. Applying Einstein's theory of special relativity, Chandrasekhar calculated that as the electrons approach the speed of light, the outward pressure they provide begins to level off. It no longer increases enough to fight the growing force of gravity. He discovered there is a precise, critical mass where the inward pull of gravity will always overwhelm the maximum possible outward push of electron degeneracy pressure. That mass, that point of no return, is the Chandrasekhar limit. The currently accepted value for a typical white dwarf is about * 1.44 times the mass of our Sun. This number, 1.44 solar masses, is one of the most important in astrophysics. It is a fundamental cosmic boundary. A white dwarf with a mass below this limit can be supported by electron degeneracy pressure and will remain stable. But a white dwarf with a mass above this limit is destined to collapse. Gravity will win. This was the absurd conclusion that Arthur Eddington so strongly rejected. Eddington's intuition, based on older physics, was that a star should always be able to find a state of balance. The idea that it could just keep collapsing seemed like a failure of the theory, a nonsensical outcome. He believed some other, gentler physical law must intervene to prevent it. The disagreement was more than scientific. It was a clash between an established giant of the field and a young, unknown student. At a famous meeting of the Royal Astronomical Society in 1935, Eddington used his position to publicly dismiss Chandrasekhar's work, a difficult moment for the young physicist. For years, the scientific community sided with Eddington, and Chandrasekhar's limit was largely set aside. He eventually moved on from the subject entirely. But physics does not depend on authority or reputation. It only depends on what is true. Decades later, as our understanding deepened, the scientific community came to realize that Chandrasekhar had been right. Eddington's hoped for law of nature to prevent the collapse did not exist. There really was a hard limit. In 1983, Subramanian Chandrasekhar was awarded the Nobel Prize in Physics for the very work that had once been so unsettling. The cosmic partner, building to an end. So, a stable white dwarf is well below 1.44 solar masses. How could one ever cross this threshold? A white dwarf, after all, is a stellar remnant. It's no longer creating more mass. The answer is found in a common cosmic arrangement, a binary star system. Most stars are not alone like our Sun. They are often born in pairs, gravitationally bound to one another. Imagine a system where one star has already lived its life and become a quiet white dwarf. Its companion, however, might still be a normal star, or an aging red giant. The two stars orbit each other, locked in a gravitational dance. The white dwarf, despite its small size, is incredibly massive and its gravitational pull is immense. If the companion star expands or orbits closely, the white dwarf's gravity can begin to pull material away from its partner. A stream of gas, mostly hydrogen and helium, begins to flow from the companion toward the white dwarf. This process is called accretion. The stolen material forms a glowing, heated structure called an accretion disk as it spirals around the white dwarf. Slowly, this matter funnels down from the disk onto the white dwarf's surface. Layer by layer, the white dwarf grows heavier. Century by century, its mass creeps upward, getting closer and closer to that number. 1.44 solar masses. The universe is now holding its breath. The white dwarf is balanced on the edge of the Chandrasekhar limit, the edge of stability. Once it crosses that line, there is no going back. Gravity will take over, and a new, final process will begin. Catastrophic flash. The type Ia supernova. The moment the white dwarf's mass exceeds the 1.44 solar mass limit, the quantum pressure that was supporting it fails. Gravity wins, and the core begins to collapse. But this collapse is a trigger. As the core contracts, its temperature and pressure rise to previously unseen levels. Within seconds, the temperature reaches billions of degrees. This is the ignition point for carbon fusion. In a massive star, carbon fusion begins in a controlled way. But a white dwarf is not a normal star. Its core is made of degenerate matter, which has a strange property. Its pressure does not increase with its temperature. In a normal star, if fusion starts to run away, the core heats up, expands, and cools, and the reaction rate stabilizes. It has a natural thermostat. A degenerate core has no such thermostat. When carbon fusion ignites, the temperature shoots up, which accelerates the fusion rate. This produces even more energy, raising the temperature further in a runaway feedback loop. But because the pressure does not respond, the core doesn't expand and cool. It just gets hotter and hotter. What happens next is a detonation. In less than a second, a wave of thermonuclear burning sweeps through the entire core. A large portion of the star's carbon and oxygen fuses all at once into heavier elements like silicon, and then into radioactive nickel and iron. This releases an immense amount of energy. This energy is so great that it completely overcomes the star's gravity. The white dwarf is utterly disassembled. The star tears itself apart in a thermonuclear explosion. This is a *type Ia supernova. For a few weeks, the light from this single exploding star can outshine its entire galaxy. The explosion throws the newly forged heavy elements out into space at speeds of thousands of kilometers per second. Unlike other types of supernovae, which can leave behind a neutron star or a black hole, a type Ia supernova leaves nothing behind. The white dwarf is gone. All that remains is an expanding cloud of hot gas, rich with the iron and other elements that will one day be incorporated into new stars, new planets, and perhaps new life. Your own body contains elements forged and scattered by such explosions. We are, in a quiet sense, made from the remains of these events. An alternate fate, core collapse and neutron stars. The type Ia supernova is the fate of a white dwarf that accretes too much mass. But it is not the only way a star can end in an explosion. In fact, this path is reserved for the remnants of lower mass stars. Stars that are born with much more mass, more than about 8 times the mass of our Sun, follow a different path. These massive stars live fast and die young. Their immense gravity causes them to burn through their fuel at a furious rate. They do not stop at fusing helium into carbon. Their cores become hot enough to fuse carbon into neon, then silicon, and finally, silicon into iron. The star's interior becomes like an onion, with layers of different elements. But this process has a final stop: iron. Fusing elements up to iron releases energy. Fusing iron into anything heavier, however, consumes energy. When the star's core becomes a ball of iron, the fusion engine at the very center of the star stops. There is no more outward pressure. This iron core is already more massive than the Chandrasekhar limit. In less than a second, the support of the star vanishes. What follows is a * core collapse. Gravity wins instantly. The iron core, perhaps the size of the Earth, collapses in on itself at 1/4 of the speed of light. The collapse is so rapid that it only halts when the core reaches the density of an atomic nucleus. The material becomes so dense that even the forces holding atoms together push back. The infalling outer layers smash into this new, rigid object and rebound, creating a shockwave that blasts outward through the rest of the star. This is a * core collapse supernova. While the trigger is different, core collapse versus thermonuclear detonation. The result is another enormous explosion that takes the star apart. But unlike a type Ia event, a core collapse supernova leaves something behind. That super-dense object that formed in the collapse remains. Depending on the original star's mass, it becomes a neutron star, or it collapses forever into a black hole. So we have 2 paths to destruction, both governed by a cosmic weight limit. For the dead cores of low-mass stars, the Chandrasekhar limit of 1.44 solar masses is the trigger for a thermonuclear explosion. For the living cores of high-mass stars, Exceeding that same limit leads to an unstoppable core collapse. Two different mechanisms, one fundamental rule. There is a point where matter becomes too heavy to support itself. A universe of rules. From a 19-year-old's calculations on a quiet sea voyage to the far reaches of the universe, the Chandrasekhar limit has revealed some of the deepest secrets of the cosmos. The end of a white dwarf in a Type Ia supernova turned out to have a remarkable property. Because they are all triggered by the same mechanism, a white dwarf crossing the same mass limit, they all explode with a very similar, predictable brightness. They are what astronomers call asterisk standard candles. Imagine looking at a row of identical light bulbs stretching into the distance. By measuring how dim each bulb appears, you can calculate how far away it is. Type Ia supernovae are the universe's standard light bulbs. They are so bright they can be seen across billions of light years. By finding them in distant galaxies, astronomers could, for the first time, accurately measure the vast distances of the cosmos. In the late 1990s, astronomers used these standard candles to measure how the expansion of the universe was changing over time. Most assumed gravity would be acting as a brake, but they found the opposite. The most distant supernovae were fainter, and therefore further away, than they should have been. The only explanation was that the expansion of the universe wasn't slowing down. It was accelerating. This was a discovery that revealed something unexpected about the universe. It meant some unknown, repulsive force was acting against gravity on a cosmic scale. This was given a name, dark energy. It is now believed to make up nearly 70% of the universe, yet we still do not know what it is. This revolutionary discovery was made possible by observing the end of white dwarfs, a process understood because of a limit calculated by a young man who was told his math was absurd. So, the universal weight limit that destroys stars does more than create explosions. It forges the heavy elements that make planets and life possible. It governs the final state of suns. And it provides us with the tools to probe the largest mysteries of all: the scale, the history, and the future of our universe. It is a quiet and beautiful reminder that even in the face of immense power, the cosmos reveals its most profound secrets. The last habitable planets in the universe. For most of cosmic history, the universe will be a cold and quiet place. Star formation will slow and then cease. The cosmos will fade into a long twilight, the great lights of the galaxies having burned themselves out. But what if that is not the end of the story for life? What if the universe has a final act, hidden in the gentle light of its most ancient, dying stars? Imagine looking at a star that has died. Not in a brilliant flash, but in a quiet exhale, leaving behind a glowing corpse, a white dwarf. For a long time, these were seen as the end of the line. Cosmic graveyards where the story of a solar system concludes. We have been told that when our own sun dies, it will swell, consuming the inner worlds, and then shrink into one of these dense, fading embers. A vision of finality. But that entire picture is changing. New discoveries are revealing that these dying stars are anything but dead. They are complex worlds with a hidden life of their own, one that stretches across billions, even trillions, of years. We are now considering a different idea: that these cooling stellar cinders could host the last pockets of life in a dying universe. Today, we journey to the end of time, to explore these last habitable planets. Worlds that might circle ghost stars, bathed in the soft glow of a universe on the brink of an endless night. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share where you're watching or listening from. To understand the last habitable worlds, we first have to understand how their stars die. The great majority of stars, more than 97% of them, including our Sun, will not end in a spectacular explosion. Their demise is a much slower, and in some ways, more graceful process. For billions of years, a star like our Sun exists in a state of balance. Gravity tries to crush it, but this is held back by the outward force of nuclear fusion in its core. But this cannot last. Eventually, the hydrogen fuel runs out. This is where the star's long goodbye begins. With the furnace sputtering, gravity begins to win. The core contracts and heats up, igniting a shell of hydrogen fusion around it. This new, furious energy pushes the star's outer layers outward. The star swells, its surface expanding, its color reddening as it cools. It becomes a red giant. For our own solar system, this will be a catastrophe. The Sun's expanding atmosphere will reach for the inner planets. Mercury and Venus will be swallowed. The fate of Earth is less certain. Some models suggest it will be consumed. Others, that it might barely escape, left as a scorched, lifeless rock. But this is not only a story of destruction. The red giant phase brings a strange, temporary spring to the outer solar system. Worlds that were once frozen wastelands will begin to thaw. The icy moons of Jupiter and Saturn might see their subsurface oceans become surface oceans. For a brief moment, the habitable zone, the region where liquid water can exist, shifts outward, creating fleeting paradises in unexpected places. This phase, however, is violent. The dying star sheds its mass through powerful winds. After a few 100 million years, the star's outer layers are finally cast off into space, forming a beautiful, expanding shell of gas called a planetary nebula. What remains at the center is the star's core. A hyper-dense, searingly hot object about the size of Earth, but with half the mass of the original star. This is a white dwarf. It has no fusion left to power it. It is simply the cooling ember of a star that was. For a long time, this was thought to be the end of the story. A solar system, scoured and empty, with a fading stellar corpse at its heart. How could life ever find a foothold in such a place? So, the star is dead. All that's left is this strange remnant, the white dwarf. Let's pause for a moment to appreciate just how strange these objects are. An object with the mass of the Sun, crushed into a volume the size of the Earth. A single teaspoon of its material would weigh several tons. It's held up not by heat, but by something called electron degeneracy pressure. A quantum rule that prevents it from collapsing any further. When a white dwarf is born, it is incredibly hot, with a core temperature that can exceed 100,000 Kelvin. But with no internal energy source, its fate is simple: to cool down. It radiates its leftover heat into space, like a hot coal taken from a fire. At first, this cooling is rapid. But then, something interesting happens. The cooling starts to slow down. Dramatically. A white dwarf's incredible density means it has a very small surface area to radiate heat from. A thin outer layer of gas acts as an insulating blanket, trapping the vast reservoir of heat in the core. After its initial fade, the white dwarf settles in for a long, slow journey into darkness that lasts billions of years. After about 10 billion years, a typical white dwarf will still have a surface temperature of around 4,000 to 5,000 Kelvin. But when astronomers began to look at large populations of white dwarfs with new precision, thanks to missions like the Gaia satellite, they found something that didn't fit. Some white dwarfs seemed to be cooling even slower than predicted. They were lingering at certain temperatures for too long. There was a secret hidden inside them. A process that was fighting against the inevitable cold. This is where the story takes a truly bizarre turn. The mystery led scientists back to a prediction made more than 50 years ago. The theory was that under the immense pressures inside a white dwarf, something extraordinary should happen as it cools. Imagine water freezing into ice. As the temperature drops, molecules lock into a rigid structure, a crystal. When this happens, a small amount of energy, known as latent heat, is released. The same thing, the theory proposed, should happen inside a white dwarf. As its core cools to about 10 million degrees Celsius, the carbon and oxygen ions stop their chaotic dance and begin to lock into place. They form a gigantic crystal lattice. The core of the dead star begins to freeze solid, from the center outwards. The white dwarf starts turning into a colossal diamond in the sky, a crystal sphere the size of the Earth. This crystallization releases a massive amount of latent heat. It's like a hidden battery kicking in, temporarily pausing the cooling process. This pause is not brief. It can stall a white dwarf's cooling for up to 1 billion years. For decades, this was just a theory. But with data from the Gaia mission, we now have direct evidence. When astronomers plotted the temperature and brightness of thousands of nearby white dwarfs, they saw exactly what the theory predicted: a pile-up. An overdensity of white dwarfs lingering at the exact temperatures where crystallization should occur. It was a traffic jam on the stellar cooling sequence. The 50-year-old prediction was confirmed. Billions of white dwarfs in our galaxy are now, quite literally, crystal spheres in the sky. But as scientists looked closer, they realized that even this couldn't explain everything. Some white dwarfs were lingering for far longer than crystallization alone could account for. This pointed to yet another, even stranger process at work. The confirmation of crystallization opened the door to a new puzzle. For some white dwarfs, the cooling delay was not just 1 billion years, but up to 8 billion years, or even longer. There had to be another energy source. The answer lies in a process that sounds like it's from a chemistry lab: sedimentation. As the carbon-oxygen core crystallizes, something remarkable happens. Heavier elements, like oxygen, tend to crystallize first and sink toward the center. This slow, massive shuffling of matter releases gravitational energy, heating the star. The effect is even more pronounced with trace elements. One key player is an isotope called neon-22. As the core freezes, this heavier neon sinks through the crystal mush toward the core, releasing a significant amount of energy and delaying cooling by billions of years. In some cases, the solid crystals that form are actually less dense than the surrounding liquid. So, instead of sinking, they float upwards. This motion creates a powerful engine that releases gravitational energy and can pause the cooling for an astonishing 10 billion years. This bizarre phenomenon, like ice cubes bobbing in a drink but on a stellar scale, is not just a fading ember. It's a thermodynamic engine, cleverly converting gravity into heat to hold off the cold. And this brings us to the most profound question of all. If a white dwarf can remain a stable, albeit dim, source of energy for so long, what does that mean for any planets that might be orbiting it? This is where the story pivots, from the death of a star to the potential rebirth of a solar system. So, we have a stellar remnant, a white dwarf, providing a stable energy output for billions of years. This raises a quiet question: could it support a habitable zone? The first challenge is how a planet even gets there. During the red giant phase, any inner planets would have been destroyed. So a planet in a white dwarf's habitable zone would have to be either a survivor from the outer solar system that migrated inward, or a second-generation planet formed after the star's death. The evidence for both is growing. Recently, the James Webb Space Telescope made direct images of what appeared to be giant planet candidates orbiting white dwarfs at large distances, proving that such worlds can survive their star's violent evolution. Simulations show it's possible for such planets to migrate inward after the white dwarf has formed. Even more interesting is the evidence for second-generation planets. Many white dwarfs are polluted with rocky materials, which should have sunk into the star's interior. This suggests they are actively pulling in material from a surrounding debris disk, likely the remains of asteroids and comets. And where there is a debris disk, there are the raw materials for new planets. Because a white dwarf is so dim, its habitable zone is incredibly close, with orbits taking just hours, not years. This proximity creates its own challenges. The most significant is tidal locking. A planet this close would have one side in perpetual daylight and the other in eternal night. For a long time, this was seen as a problem for habitability. However, recent climate models have changed this view. Research from astronomers like Aomawa Shields has shown that a thick atmosphere could redistribute heat from the day side to the night side, creating a stable and potentially habitable climate. In fact, for a planet orbiting a white dwarf, fewer clouds would form on the day side, allowing the planet to absorb more heat and stay warmer than previously thought. The area along the terminator, the twilight zone between day and night, could be a particularly gentle place for life. The picture that emerges is one of a bizarre but potentially stable environment. A world bathed in the perpetual twilight of a tiny, ancient sun. A world where day and night are fixed places, not times. It is a far cry from Earth, but it is a world where the conditions for liquid water, and therefore life, could persist for billions of years. This brings us to the heart of our journey. We have a stable, long-lived energy source. We have ways for planets to get into the right orbit. And we have climate models that show these planets could be genuinely habitable. The key is the incredible longevity of this habitable zone. While the zone does move inward as the star cools, the process is incredibly slow. Thanks to the cosmic hacks of crystallization and sedimentation, a planet could remain in the habitable zone for nearly 7 billion years. To put that in perspective, life on Earth has existed for about 4 billion years. For the rarest white dwarfs, the habitable zone could persist for 10 billion years or even longer. These are timescales that approach the age of the universe itself. What would life on such a planet look like? It would adapt to a different kind of light, which is bluer and has more ultraviolet radiation. The constant, unmoving sun would mean no day-night cycle. Biological rhythms would have to evolve based on other cues. Life on the permanent day side might live in water for shielding, while life in the twilight zone would experience a perpetual sunrise. And the best part? This isn't just speculation. We may soon have the ability to find out. The James Webb Space Telescope is powerful enough to study the atmospheres of Earth like planets transiting nearby white dwarfs. Because the star is so small, the signal is much easier to detect. With just a few hours of observation, JWST could potentially find biosignatures, gases like oxygen and methane, that could indicate the presence of a living world. We are on the cusp of being able to look for life on these ghost worlds. The story of the universe may not end in the cold, silent darkness we once imagined. We've journeyed from the violent end of a sun-like star, through the formation of its dense, crystalline remnant, and uncovered the strange physics that granted a second life. The challenges are immense, but the science now shows that none of them are insurmountable. We've gone from dismissing these systems as sterile graveyards to seeing them as a new and promising place in our search for life. These last habitable worlds, circling their dim, ancient suns, would be the final inheritors of the cosmos. Long after the great galaxies have dissolved and the sky has gone dark, these tiny points of light could be the last places where the universe is aware of itself. We began by staring into the dying embers of the cosmos, expecting to find an ending. Instead, we may have found a new beginning. And it raises a final, quiet question. As we peer into the twilight of the universe, are we seeing a preview of our own distant future, or are we perhaps, finally, about to learn that we are not alone? If you enjoyed this journey to the end of time, thank you for watching. And I have to ask, what do you think life on a planet with a permanent day and night side would be like? Let me know in the comments below. The strange star that shrinks when it gets heavier. In the universe we observe, there are fundamental principles. Principles learned from daily experience. When more material is added to an object, it becomes heavier, and it grows larger. It is a simple and intuitive logic that governs our world. But in the cosmos, the rules are not always familiar. In the silent expanse where the lives of stars conclude, there exist objects that defy this logic. These are stellar remnants that operate on a different principle. The more mass they accumulate, the smaller and denser they become. This is not a riddle. It is a consequence of the laws of physics operating under conditions of extreme gravity, a contest between the force that shapes galaxies and the unyielding rules of quantum mechanics. To understand this paradox is to explore the absolute limits of matter itself. This is a journey to the end of a star's life, and into the physics that governs its remains. Our journey begins at the final phase of a star not unlike our own Sun. For billions of years, it exists in a state of equilibrium. In its core, a nuclear furnace fuses hydrogen into helium, and the outward pressure of this energy perfectly balances the inward crush of gravity. But this fuel is finite. When the hydrogen is depleted, the outward pressure weakens, and gravity begins to dominate. The core collapses, and this collapse ignites a new phase of fusion in a surrounding shell, causing the star's outer layers to expand. The star transforms into a red giant. After this phase, its life ends. It releases its outer layers into space, forming what is known as a planetary nebula. What is left behind at the center is our subject, a small, hot, and incredibly dense core. This is a white dwarf. It is an object that can contain half the mass of our Sun compressed into a volume no larger than the Earth. It no longer generates new heat. It is a cooling ember, destined to radiate its remaining warmth over trillions of years until it becomes a cold, non-radiating body, a theoretical black dwarf. Yet, within this stellar remnant, a silent force prevents its complete collapse, a force born not from heat, but from the fundamental nature of matter. Inside a white dwarf, gravity is relentless. Without the outward force of fusion, classical physics suggests that the star's mass should collapse into a singularity. But it does not. Something is pushing back. That something is called electron degeneracy pressure, a phenomenon that can only be understood through the lens of quantum mechanics. At the subatomic level, the universe is governed by strict rules. One of these is the Pauli Exclusion Principle, formulated by the physicist Wolfgang Pauli. It states that no two electrons can occupy the identical quantum state in the same space. Imagine each quantum state, a combination of energy level and spin, as a unique seat in a vast arena. As electrons fill this arena, each must find its own empty seat. In the extreme gravity of a white dwarf, electrons are forced together. All the low-energy states are quickly occupied. To find an available position, other electrons are forced into progressively higher energy levels. These high-energy electrons move at immense speeds, not because they are hot, but because the quantum rules leave them no other available state. This motion generates a powerful outward pressure. It is a cold, quantum force that persists even at a temperature of absolute zero. It is a fundamental barrier erected by the laws of physics, halting the crush of gravity. For a time, here we arrive at the central paradox. Many white dwarfs exist in binary systems orbiting a companion star. If they are close enough, the white dwarf's powerful gravity can pull material from its partner in a process called accretion. As the white dwarf feeds, it gains mass. Our intuition suggests it should grow larger. Instead, it shrinks. The reason is that more mass means stronger gravity. The entire star is compressed with greater force. To counteract this, the electron degeneracy pressure must also increase. This is achieved by forcing the electrons even closer together, which compels them to occupy even higher energy states. This tighter packing results in a smaller stellar radius. Observations have confirmed this mass-radius relationship. A white dwarf with approximately half the mass of our Sun has a radius about 1.4 times that of Earth. But a white dwarf with a mass just over that of our Sun shrinks to a radius smaller than Earth's, around 0.7 times its size. More mass results in less volume. It is a demonstration of the contest between gravity and quantum pressure. But this process has a limit. As a white dwarf accretes matter, the electrons within are forced into ever higher energy states, moving at speeds that approach the speed of light. Here, a third physical principle becomes critical: Albert Einstein's theory of special relativity. It dictates that no object with mass can reach the speed of light. As an electron approaches this cosmic limit, adding more energy ceases to increase its speed significantly. This has a critical effect on electron degeneracy pressure. As the most energetic electrons approach the speed of light, the pressure they generate begins to plateau. It no longer increases at a rate sufficient to counteract the ever stronger pull of gravity. The quantum barrier begins to falter, while gravity continues to grow with each particle of accreted matter. The system is set for a catastrophic failure. In the 1930s, the astrophysicist Subrahmanyan Chandrasekhar calculated the consequences of this effect. By combining quantum mechanics with special relativity, he determined that there is a maximum possible mass for a stable white dwarf. Beyond this point, electron degeneracy pressure will fail, and collapse is inevitable. This critical threshold is now known as the Chandrasekhar limit. Initially, this idea was met with resistance. The concept of a star collapsing under its own weight was considered by some to be an absurdity. But Chandrasekhar's calculations were correct, and for his work, he was eventually awarded the Nobel Prize in Physics in 1983. The limit is approximately 1.44 times the mass of our Sun. Below this mass, a white dwarf can remain stable for eons. But the moment it crosses this threshold, its collapse begins. When a white dwarf breaches the Chandrasekhar limit, one of two fates awaits it. The first, and most common, is a thermonuclear detonation. Most white dwarfs are composed of carbon and oxygen. As the star begins its final collapse, the pressure and temperature in the core spike, igniting a runaway chain reaction of carbon fusion. In a matter of seconds, the star is consumed in a massive explosion, a type Ia supernova. The event is so luminous it can briefly outshine its entire host galaxy, and it completely obliterates the white dwarf. These explosions are crucial tools for cosmology. Because they all occur at almost precisely the same mass, they have nearly the same intrinsic brightness. They serve as standard candles, allowing astronomers to measure vast cosmic distances. It was by using these supernovae as mile markers that astronomers made a profound discovery: the expansion of the universe is accelerating. There is a second, rarer possibility. For some white dwarfs with a specific composition of oxygen, neon, and magnesium, the collapse can proceed differently. The pressure becomes so extreme that electrons are captured by protons in the atomic nuclei, combining to form neutrons and neutrinos. This process, called electron capture, removes the very electrons that were providing the degeneracy pressure. The quantum barrier vanishes. The core implodes, collapsing from the size of a planet to a ball of neutrons just 10 to 14 kilometers across. This is not a thermonuclear explosion but a core collapse event, which can also trigger a supernova, though a much fainter one. What is left behind is no longer a white dwarf. It has transformed into a neutron star. The story of shrinking stars does not end here. The creation of a neutron star takes the paradox to a new extreme. It is an object of almost unimaginable density. A mass 1 to 2 times that of our Sun is crushed into a sphere the size of a city. A single teaspoon of its material would weigh billions of tons. This object is supported by a new force: neutron degeneracy pressure. Neutrons, like electrons, are subject to the Pauli Exclusion Principle and resist being forced into the same quantum state. They create a new quantum barrier, one that is orders of magnitude stronger than the one inside a white dwarf. And the paradox continues. Neutron stars also follow a mass-radius relationship where more mass leads to a smaller star. For the same reason, greater gravity requires tighter packing to increase the degeneracy pressure. But even this force has a limit, known as the Tolman-Oppenheimer-Volkoff (TOV) limit. Current understanding places this limit between approximately 2 and 2.5 times the mass of our Sun. If a neutron star exceeds this mass, no known force in the universe can halt its collapse. It implodes completely, crushing down to a point of infinite density and tearing a hole in the fabric of spacetime. It becomes a black hole. This journey from a stable star to a shrinking white dwarf, to an even smaller neutron star, and finally to a singularity, marks the ultimate victory of gravity over matter. This process, while distant, is deeply connected to our own existence. Type Ia supernovae are the universe's great forges for elements like iron. The iron in our blood was likely created in such an event. The mergers of neutron stars, and possibly the collapse of certain white dwarfs, are thought to be the primary source for the heaviest elements, like gold and platinum. These objects are also cosmic laboratories. Their interiors contain matter under pressures and densities impossible to replicate on Earth. By studying them, we test the limits of our most fundamental theories. They are the proving grounds where our understanding of reality is pushed to its extreme. Finally, in the deep future, long after the last stars have faded, the universe will be populated by these remnants. Understanding their stability is to understand the final state of the cosmos. We began with a simple observation that is true in our world, but not everywhere. The answer has led us to the edge of physics, through the life of a star, into the strange rules of the quantum world, and to the final battle between gravity and pressure. The shrinking of a white dwarf is not a curiosity, it is a fundamental lesson written in the stars. It reveals a universe that operates on principles far stranger than our intuition can grasp. It is a story that ends either in a brilliant explosion that seeds the cosmos with the elements of life, or in an irreversible collapse into an object of impossible density, a quiet reminder that the most profound truths of the universe often defy the world we think we know.